Good morning, participants. Today, day two, we are starting the sessions. We are starting the day two sessions, and today's session is by Dr. T Ramesh sir from NIT Andhra Pradesh, Tadepalli. So, before starting the session, we are welcoming the sir by bouquet.
Thank you, sir. So, thank you, Vidyanlal Management and the Department of Electrical Engineering and other faculty members for inviting me for this FDP. Today will be this is the topic is taken from the today's session, and so I'll try to cover this topic, and these are the contents which will be delivered in this topic. Okay. Okay. So we will see the maximum all the content we will discuss, and if time permit, we will also see how to draft a research proposal and how to write a paper. Also, we will discuss at the end of the session. And basically, nowadays, the trend is moving towards the electric vehicles. So, why we need to go for the electric vehicles? So, basically, you'll get to know from the upcoming slides. So, basically, if you see this slide, so here in this slide, so this is the carbon footprint of 100%, from which part we are getting the carbon footprint more. So basically, one is the transportation, it's captured of 34.3%, and then electric power, which is generating the power, so it is 38.4%. So here the transportation itself taking 34.3%. So imagine how much pollution we are releasing into the globe. So that is 34.3%. So how can we minimize this carbon footprint? So there is a alternative to reduce this carbon footprint is that we need to convert the internal combustion engine based vehicle into the electric vehicle. So the electric vehicle is the 100% green if it is being charged from the power generated from the renewable energy sources. So the electric vehicle will not release any carbon footprint. So if we convert the IC based engine into the electric vehicle, then this portion can be minimized. So this portion can be minimized, thereby we can get the natural air. So from where the electric vehicle was inspired? Basically the electric vehicles are inspired from these toys. So basically this vehicle is been run by the DC motor. It is being fed from the battery. Okay. So the same concept was introduced for the electric vehicle. So why it is more preferred compared to the IC based engine? Because see the air quality in Indian cities. Basically the this study was made by the every year IQ air study. In every year it is implemented. So in the 2020 you can see the our Indian capital New Delhi placing a top position. And not only 2020, 21, 22, 23, 24, and 25 also. So every year, the New Delhi capital of our country is placing a top position, and you see, we are experiencing recently the Delhi government has closed the schools for 10 days, 15 days because of the pollution rate increase drastically. So how can we reduce that pollution? So we cannot shut down the industries because which are required for the country development. So what is the alternative? So the alternative thing is that we can convert the IC based engine to the electric vehicle so that we can somehow decrease the carbon footprint in that location. So recently we were experienced in the New Delhi. The government of Delhi has implemented the odd even rule. So because of this odd even rule, they have able to reduce the expected output and they have reduced the carbon footprint because of that odd even rule. It says that if the number of vehicles running on the roads decreases, then the carbon footprints are decreasing. So it means if we decrease the IC based engine, then the air will we will get the air quality air. Okay, so this is the one of the alternative. That's why we need to go for the electric vehicle instead of IC based. And not only Delhi, you see the Mumbai, Bangalore, Hyderabad, Chennai. These are the major cities of our country, and which are placing top in, day by day because the pollution rate is increasing drastically day by day. So the one of the alternative to decrease this pollution is to convert IC based engine into the electric vehicle. So this is the source I have taken from the DE2. And not only pollution rates, so because of this pollution rate, there are lots of deaths happening in our country. So compared to other countries, though the population of our country is very high, so that is also one of the reasons why we placed the top instead of other countries. And but the population wise, India and China is more or less same. But if you see the our death rates compared to China is more because now the China is far ahead compared to the India in technological development and then implementation also. So now almost majority percentage of the electric vehicle being run by the manufacturing and then sold by the country that is China. Still today it is in the top position. Even the developed countries, advanced countries, USA is behind the China in electricity. So you see the image does here and before pollution, after the pollution. So how can a public survive in this such kind of situation? So if you be calm, if you stay at home, then the nature will be resolve itself. So this is the second image we will get when there is no pollution. And so, how can we reduce these carbon footprints, carbon emissions? So, there are advanced technologies. With these advanced technologies, we can further reduce these carbon footprints. So, the first one is the advanced internal combustion engine. Instead of the IC based engines, if you use the advanced internal combustion engines, then somehow we can reduce the up to 15%. And if you go for the natural gas and biofuel, we can reduce between 10 to 30%. And if you implement the vehicles of hybrid, that is fuel plus electric, then we can decrease the carbon footprint 30 to 40%. And then if you go for the fully electric, then it's all battery based, then we can somehow reduce the 50 to 100%. Then hydrogen based also it gives the 50 to 100%. Then as I always says the future will be for a electrical engineers. It means the future is electric. So what is that? So lifetime fuel consumption. If you take one example, so in a lifetime of a car which we are using, so it may burn the 30,000 liters. Imagine that we are burning 30,000 liters. Then the cost we are spending almost more than 30 lakhs. Now the price is 110 rupees. Some states 115 also. So in that ratio, it is the more than 35 lakhs. It is in case of the IC based engines. Now, if you go for the fully electric, then we will charge for a entire life the 70 megawatt hour power we will charge. Then the cost we are spending for that one charge is the 4.2 lakhs. So now you see the difference between these two. The payback period from the electric we are getting means within a short period of time, whereas we are spending the amount for the IC based engines are more. So this is the one of the beauty of the electric vehicles. Then the rising of the fuel prices. If number of electric vehicles are number of IC based engines are increasing, then we need to import the fuel from the outside because we don't have such kind of metals in our country. So we need to depend on the certain countries. So thereby, day by day, the charges of the fuel are increasing. So now the cost is increased to $120 per barrel. So day by day it is increasing. So if we convert it to the EV, then definitely this cost will be decreases because we will import less amount of the oil. Then the other countries definitely they reduces the cost of the oil. Then thereby we can support for the our economic growth. So that is the one of the advantage and then environmental impact. So if you go for the EV, then there is no harmful in the atmosphere. And IC based engine, we are releasing the carbon footprint in the atmosphere. Then falling prices, so day by day EV cost is reducing drastically that attract the consumers more. Then what is the history of the electric vehicle? The history of the electric vehicle started long back, basically in the year of 1841. So inventor Robert Davidson has started, he has built a bigger electric flying car in 1841. So after the almost 40 years of his invention, the inventor Thomas Parker has built one first manufacturing electric automobile in London. Then the first electric car was produced in the USA in the year of 1890. So the electric vehicle has its history of long, means it started in 1837. Now, what are the major factors that attract electric vehicles? Why people need to go for the electric vehicle? The first point is the reliability. So, what is the reliability we are getting here? So, the reliability we are getting here, see, in the electric vehicle, the number of parts in the electric vehicles are less. The major parts are drive, that is motor, power converters, and the gear. So these are the very less parts available in the electric vehicle. So these parts require the less maintenance. The AC motor which we are using in the EV vehicles, which hardly require maintenance. Okay, so and the power converters also giving the best output. So the electric vehicles require the less maintenance. Thereby, we will get the good reliability from it and then flexibility. What is the flexibility? Different consumers require different types of EVs. Means the models. So nowadays, different models are attracting the people. Okay, and then size wise also day by day nowadays the bigger SUVs also being implemented in the EVs. So the people are attracting more in the flexible manner. So the OEM means the manufacturing industries are manufacturing the electric vehicle in different sizes. Thereby people are attracting more. Then growing infrastructure. So day by day the charging infrastructures are increasing a lot. So we are experiencing the growth of the charging infrastructure in our country. So thanks to the government of India, they are investing a lot nowadays in the charging infrastructure towards the highway. Thereby, people will be motivated and they will start purchasing the EVs. So that is the stand for the government of India and affordability. So the other major factor that is affordability. So we can attract the people, the medium level people. Okay, so the salarized people, they can afford 9 lakhs to 15 lakhs in the range. Okay, nowadays the cost of the electric vehicle and the IC based engine vehicle, which oil based engine vehicles, are more or less same. Okay, so the people are affordable to purchase the electric vehicle because the Tata Tiago is coming the around 10 lakhs. So people are ready to afford that much cost. And then the another advantage we will get the public health because the EVs won't release any gases and it will be increasing the public health. Then here I have taken one example. This is the data of long back because the cost of the vehicle I have taken tentatively. So here there are three kind of vehicle I have compared. The first one is the lithium ion based two-wheeler, and the second one is the lead acid based two-wheeler, and then last one is the petrol based vehicle. So now over a span of 5 years, a person traveling 50 kilometers on an average a day. So how much cost will be spent by a person when he is traveling on an average 50 kilometers in a day? So in a 5 years span of time, so he is spending for the lithium ion is the 1,13,000 and the lead acid 91,000 and then petrol based vehicle is 1,75,000. So now you can see the saving of this one. So here lithium ion based vehicle means electric vehicle we are saving 61 lakh and lead acid we are saving of 91. Not only we are saving the cost, we are also saving for the means we are reducing the environmental impact. And electric vehicles sales. So electric vehicle means not only two-wheeler, three-wheeler, and a four-wheeler. There are trucks means the transportation purpose. Okay, so in a daily wages we need to have a trucks which transport the from one place to other places. So nowadays the trucks being converted into the electric vehicle. Okay, so here the percentage of the electric vehicle in terms of the vans and trucks is 3% entire world globe, and the passenger cars are 14%, buses are 38%, and two-wheeler and three-wheeler are 49% share of the sales. And the passenger EV sales by the year of 2020. So see this picture. So now you see the picture here. The China at the year of 2020, 1.33 million vehicle has been sold by the China. The entire Europe country sold 1.39 only. So entire Europe country sold 1.39. The China itself sold the electric vehicle is 1.33 million. It means see the how China is dominating the EV sector. Okay, so still today also the China is dominating the EV sector, and we call the advanced country. So the United States is standing at 328,000, and global stock electric vehicles stood at 17.7 million by the year of 2021. So here you can see the portion of the China. You can see the long band of the China compared to other countries. And 6.5 million electric cars were sold in the 2021, and still in the 2021 also China is placed in the top position. And this is the electric vehicle share rapidly increasing. You can see the early adopters are like China is the early adopters, and then Belgium, France, United Kingdom, and Portugal. These are the countries were implemented the EVs and then taken into the public. These are the countries like USA is tested later on compared to the China, and these are the heavy users. Basically, these countries, Switzerland, they are using the electric car sales more, and these countries too. And then the electric vehicle rapidly shifting from push to pull. What is difference between push and pull? Basically, earlier the government are running behind the public. So purchase the electric vehicle, we will give you the incentives in terms of tax rebate, or we will reduce the cost of the electric vehicle. So government is pushing to public to purchase the electric vehicle. But now the current generation, the current trend is that the people have the awareness that the what is the advantage we will get from the electric vehicle, and how we can support the environmental growth. So in that direction, people are thinking and they are going for the electric vehicle purchase. So it means pull. So here the consumers are spending more than the government. Okay. So here you see the $250 billion the consumers are spending. The government is spending only 30 billion. Okay, so this is the ratio. So nowadays there is a huge awareness between the people and they are going for towards the EV. And this is the passenger EV sales by year of 2022. It is still increasing by 2022. You can see more than 10 billion. And then EV sales by the year of projected 2023. So 2023 almost 14.5 million electric vehicles. And large models and SUVs are dominating. So basically, the people are showing much interest in the SUVs and the large vehicles. If you see the majority sales in the China, majority sales are SUVs. Okay, so they need the comfort and they are going for the SUV vehicles. But when people are going for the SUV vehicles, then we need to the electric vehicle cost will be increases. Why? Because the SUVs are required the large amount of the batteries. Okay, so the majority of the minerals are consumed by the this SUVs, the larger vehicles. Okay, because it requires the high capacity of the batteries. Okay, so most of the minerals are consumed by these SUVs, thereby it is supporting the cost increment of the electric vehicles. And transport electrification is not only about the cars. As I said earlier, so the means public transportation, buses and then trucks, vans are being converted into the electric vehicles. Right, you can see the year wise from 2019 to in the 2019 we will find the rarely find medium duty trucks and the step van, the very small portion, small amount. But if you see the 2025, you can see that here we were having the large amount of electric vehicles being sold in terms of trucks and the step vans. And then heavy duty trucks. So this is for the transporting the goods from one location to the another location. So heavy duty trucks they will use. So this is being used with the electric vehicle. And what is the India standing compared to the world push? So by the year of 2090, we were standing at 0.07 percentage. When the Norway is a small country, it's ahead of us. That is 13% vehicle being operated by electricity in their country. Of course, ours is a populated country, and the ratio of the point 7 will be around 49,000 every vehicle. But compared to this country, we were far behind. Okay, but this scenario has been changed by the year of 2023, 2024. We were ahead of the Norway because of this government incentives. Okay, the government policies. So to attract the public, government, all the governments are implementing certain policies. So the government of USA have the policy of Inflation Reduction Act. Thereby, people are attracting more, and then Europe having the Green Deal Industrial Plan, their Net Zero Industry Act. Likewise, they were having different policies to attract the consumers towards the electric vehicle. Likewise, the India having the production linked incentive. Okay, manufacture here, sell here, and export from here. Okay, so in that way, the government of India is providing the policy of production linked incentive. And then not only the government having this policy, the all the state government having its own policy. So multiple states having multiple policies to attract the more OEMs, EV manufacturing OEMs. So likewise, India we were having the production liquid incentive scheme, and basically the EV strategy has been made by our country India long back. In the year of 2010, the Indian government announced a strategy to reward OEM with a budget of 950 billion rupees. But unfortunately, by the year of 2020, it was cracked. So when the China started, the country India also started at the same time when the China was started. But unfortunately, China has taken further. The country has cracked by the year of 2021. Then the government of India again rethink about the EV policy, and they have made one policy, that is the Indian government has established a National Electric Mission Mobility Mission Plan, that is NEMMP 2030. Okay, in the year of 2015, they have implemented a FAME Scheme 1, the faster adoption and manufacturing of hybrid and electric vehicle scheme 1, and they have launched in the year of 2015. Basically, it is a 2-year plan, but they have extended it up to 2019. In this plan, they have spent 900 crore rupees. So so, in this scheme, they have not given any condition. It should be an electric vehicle, whether it is a lead acid based vehicle or lithium battery, irrespective of the type, they have given a incentive. So, it is up to the 2019. Then, in the 2019 April 1st, the government of India has implemented the Phase 2 scheme. In this scheme, around 10,000 crores has been allocated. But here certain restriction has been imposed. What are the restrictions? It is the EV must be a lithium ion battery. At least a lithium ion battery. Lead acid batteries will not be considered to give the incentives. That is the first criteria. Then the second criteria is that the vehicle must become a speed within a short time of so it must become 80 km per hour the speed within a 2 seconds or 3 seconds, like that certain condition has been imposed in the phase 2 scheme. So this scheme is went up to the 2024, and again recently in the 2024 end the government of India has launched and given the rename, that is the Prime Minister E-Drive scheme. Okay, so in this Prime Minister E-Drive scheme, the government of India has announced around 11,000 crores. So this 11,000 crores has been announced to give the OEM as incentive, and this is a 2-year plan. Okay, so it will boost the electric vehicle into the our country, and it will attract the consumers more. But they have categorized the different ways, like two-wheeler, three-wheeler, four-wheeler. They have allocated the budget in each type. So majority of the budget, around 4,300 crores, has been allocated for the buses. It means the public transportation. So any state government can purchase the electric buses. They'll get around 50 lakhs rupees as incentive from the government of India. Okay, so majority budget has been allocated for the public transportation, because people will get more awareness when they travel through buses, or when the buses are being running in the roads on the road, then people will be more awareness will go into the public. So that is the government strategy. And then around two wheelers has been given 1700 crores, and then four wheelers has been given different amount, that is 2000 crores, and the charging infrastructure also given around this is the testing agency accreditation, that is 780 crores. Likewise, the amount has been allocated for the e-ambulance, also given 500 crores. Okay, so this way they are distributing these 1100 crores in different ways. And not only the government of India has policies, every government has implemented its own policies to attract the more OEMs. Okay, so the discussion, each all the government, majority government like Telangana and Karnataka, they were discussing with the Tesla also. Okay, so they were discussing to attract the Tesla to their state. Okay, so the government of Delhi has recently given a order to purchase the 2026, means 2026 electric buses, and it will be run by end of this year. Okay, so how much they are spending the on electric buses by the government of Delhi? Okay, so they will able to reduce the 14 lakhs 50,000 tons of carbon dioxide in the next 12 years. So likewise, all the governments are making certain policies to increase the EV growth, and the policy implement is catching the with the targets. Okay, and then the day by day the growth of the EV is increasing, and then electric vehicle market in India. So we, if you follow the LinkedIn, we always see this fellow, the Honorable Transport Minister Highways. So this fellow always we will see in the LinkedIn because they are always supporting the EV growth. Okay, and then EV sales in India from the 2016 to 2020. So it is increasing rapidly. And now you see the sale of the different vehicles, four-wheeler, two-wheeler, and three-wheeler. So compared to 2021, so 100% increase in the 2021 compared to 2020. Here 2,800, then in the 2021 it is almost 6,000. And then passenger EV sales by 2022, it is increasing a lot. It means in India, lots of EV being purchased by the consumers. And then this is because they are attracting, because the number of charging stations were built in the towards the highways. Okay, so charging stations are increasing, thereby EV sales are also increasing. Because consumer always think that, so if I purchase a EV, then if I want to travel at 200 kilometers, then how can I travel one time with the one time charging? So in between they will see the charging station to refuel the vehicle. Okay, so the government is thinking in that direction to create more charging infrastructure towards the highways so that public will attract more. And then EV sales in the from 2022 to 3 to 24. So you can see the picture. So every month strategy it is given in terms of two-wheeler, four-wheeler together. So from August 2023, it is 1,20,000, and August 2024 1,56,000 EV sales. It means the EV sales are being increasing from 23 to 24. And this is category wise from August 2024 sales of two-wheeler, three-wheeler, four-wheeler, etc. And then OEM wise also we have taken the pride of the India, the Tata Motors. Okay, so they are placing top position and they are capturing the sharehold of the 64.5%, and then MG Motors India is capturing percentage of 21%. And then OEM wise, bus sales also Tata Motors placing a 47.3%, and then Green Tech which is 36%. And then e-rickshaw also, and then India's top two-wheeler. So these are the two-wheeler side, and the majority states. Which one is the far ahead? The Kerala state is the far ahead compared to the other states. The Kerala has its percentage of 13.5, the Karnataka is 11.6, and then Maharashtra is 10.6, Telangana is 9.4. So likewise, the every state government is moving towards to the EV, and because of their policy, people are attracting more, and then battery supply chain. So as I said earlier, the SUVs are dominating nowadays. So because of these SUVs, the lots of minerals are being utilized in the SUV batteries, because SUVs are required the huge amount of batteries. So thereby the cost of the batteries increases. So this is the reason why the EV rates are not decreasing, because the majority portion is going towards the battery. And the lithium ion minerals are cost of the lithium ion minerals are increasing a lot, because nowadays most of the vehicles are using lithium ion batteries. And then thanks to Amar Raja, he has started Amar Raja Giga Corridor in Telangana state, and they are aim to spend 9,500 crores by the year of 2030. And likewise, many OEMs are coming forward to establish their manufacturing corridor, like Gujarat and all state government they are enhancing. And then you can see the market over a couple of years. So by the year of 2025, so the market growth will be huge. Okay, so being an electrical engineer, you consider either battery side, battery technology side, the drive side, or the power converter side, so or solar side. So any of this side technology you consider, then you will have a better future for your career. And as I said, so you can concentrate any of this technology, the charging station side. So how can we attract the people? It means how can we send the information? Suppose one charging station is there, but there are 10 vehicles are in a queue. So how can we attract the public? So more user friendly. So we need to send the information to the public, like this charging station having a 10 vehicle in a queue, but another charging station of nearer to the 1 kilometers that having the only one vehicle in a queue. So better you can utilize that charging station. So we need to create a program so that we can drive a public to the another charging station instead of waiting here. So we need to have a certain programming mechanism. You can think in that direction, and you can have a better future in this aspect also. Or you can design a converter, or you can go for the battery. So how can we reduce the size of the battery? So you can think in that direction, then you will have a better opportunity. Or how can we reutilize the usage battery? Okay, so or how can we reduce the size of the motor? Okay, how can we use the best utilization of the motor? How can we increase the torque density? So in that direction also you can think. So these are the areas which attracts you and give you the better future tomorrow. And which EV is right? Of course, these are the known things. So EV is better if you travel on an average 50 kilometers in a day. Then you go for the EV. If you travel less than 5 kilometers or 10 kilometers in a day, then your spending amount is more than the gaining the benefit. Okay, so if you are traveling on an average 50 kilometers in a day, then EV will be the best for a consumer. Otherwise, the EV will be the costlier. And should I go for the used one? You should not go for the used one. If you go for the used one, the more cost we are spending in the EV is battery. So battery has a certain lifetime. So manufacturer is to give maximum 5 to 8 years. Okay. So if you purchase after the 5 years, then the half of the cost of the vehicle is goes to the battery. Then again you need to spend the same amount which you have purchased. And lower lifetime cost, and lower maintenance. As I said, number of parts are less, so we don't require much maintenance here. But whereas the IC based engines, we always go need to go for 5,000 kilometers or 3,000 kilometers or 2,000 kilometers. So there will be one chart, so timeline. So we need to follow that timeline, and we need to go for the service. Okay, and the key players of the EV market. So these are the key players of the EV market: the Tesla, Audi, and BYD, etc., etc. And the Tesla is placing top, but recently in the China, the BYD is dominating compared to the Tesla, because of the rates of the Tesla vehicles are more compared to BYD, but the comfortness given by the BYD is okay, more or less compared to the Tesla. That's why people are moving, attracting more towards the BYD because the cost of the BYD is less compared to the Tesla.
BYD belongs to which country, sir?
China. So people are attracting more. Okay. And EV market key players in India. So these are the EV market key players. And the electrical dilemma. So basically, as of strategy I have taken from the Ministry of the Power, so Core Vision 2030. So by the year of 2019-20, the how much power we are generating through all the generation like nuclear, thermal, hydro, etc., etc. We were generating the 1 crore 38 1 lakh 38,910 crore units. But how much we are demand? We were demanding of 1 lakh 39,766 crore units was the demand. It means already we were having a shortfall of 16,000. Now the government of India is attractive means giving the point like convert the IC to the electric vehicle, but this electric vehicle need to be charged. So how can we charge? Already we were having 60,000 crore units of shortfall. So if you charge the electric vehicle, then we need to generate a more power. So if you generate a more power through the thermal, then what is the advantage we will get from the EV? So earlier we were burning the fuel to run the IC based vehicles. Now we are burning the coal to charge the electric vehicles. So we are standing at the same position. So instead of charging the vehicle from the power generated from the thermal, so you can move towards the renewable energy sources so that we can make the EV as green. We always say EV is the green, but really EV is the green. So battery after the certain 5 years, what we will do with the battery? There are lots of questions arises. Okay, how can we decompose those batteries, used batteries? And the second, how can we charge the battery vehicle? So from which power we will charge? The same power which we generated from the by burning the coal. So these are the many questions arises. Is EV is the really green? The EV is really green if you charge the vehicle through the power generated from the renewable energy sources, maybe solar, wind, or hybrid. Okay, so this is government need to think in this direction too. And the different types of EV. So in the literature and in the market, we will find the three types of EVs: the battery EVs, hybrid EVs. The hybrid means both battery and then IC based engines. Okay, so the middle end people want to travel 400 kilometers in a day, but they are not affordable to the SUVs because the cost of the SUVs are more. SUVs can be traveled around 400 to 500 kilometers, but they are not affordable that much. So they can go for the hybrid. So that is both battery and then IC based engine they can have. Or fuel cell it is again costlier. And then types of EVs, we were having different types of EVs and how the EVs are designed. So, and this is the power module, how it looks like the combination of the motor, inverter, and then power delivery module is assembled in the EV. So, this is the picture I have taken from the electric vehicle, Ford electric vehicle, and this is the Nissan electric vehicle. For the reference purpose, I have taken. And this is the series hybrid electric vehicle. And here we will see the series hybrid and electric vehicle. Both IC based engine will be there, battery will be there, and with the help of these two, we will ride the vehicle. And this is the example of hybrid. And then as we are using the battery, so we need to have a power trans converters. So in the EVs and hybrid electric vehicles, the power trans converters majorly used. And then why electric motors in vehicle applications? So why we need to go for the electric motors? So instead of the IC based engine, why people are going for this EVs? So in the EV, one of the we can say motor is the heart of the EV. We can say. So why people are going for the motor instead of the IC based engine? The only one thing is that the motors are required less maintenance and the motors will give you the good efficiency. Motors are reliable. Okay, so these are the features of the motors. So that's why EVs the major advantage we will get from the motor. And this is the schematic diagram I have taken for the reference. And we will see from the we will go towards the motors now. So in the literature we have different types of motors, that is AC drives and the DC drives. Before 1990s, most of the industries are using the DC motors in their industry applications. Why they were using the DC motors? Why not the AC motors? Because the DC motors are the best control motors. As today also, the DC motors are best, but because of their drawbacks, because of their huge maintenance required, DC motors are being replaced by the AC motors. Otherwise, the DC motors are the best in terms of the control. So, thanks to the advanced control techniques, so because of those advanced control techniques, AC motors are operating like a DC motors, and then most of the industries are converted this DC motor into the AC motors. So, yeah, over a period of years from 1990 to 2025, most of the DC motors are replaced with the AC motor because of the beauty of the AC motor. And then we can see what are the advantages we will get from the motors compared to the IC based engines. So these are the characteristics. The first characteristics, we will have a number of moving parts in the IC based vehicle will be very high, and the electric motor, as I said, shown in the previous slide, we will find only few: motor, and then power converter, battery. These are the main parts of the electric vehicle. So we will have a less parts. The reliability, as we are using the motors and the power converters, then we will have a high reliability. Then efficiency. The AC motors are giving the best efficiency from 80% to 95% efficiency we can get when we are using for the AC motors like induction motors, EMSM motors. And noise and vibrations, so as number of parts are less, so obviously the noise will be very less. So now recently I have read somewhere in the Google, uh, uh, certain people are thinking to add to the vehicle, means when the vehicle is coming on the road, people are not realizing one vehicle is coming behind us, because the electric vehicles will not give any sound. Okay, so no noise. So they are unable to recognize some kind of vehicle is coming behind us. Okay, to uh, uh, to avoid those kind of things, certain people are thinking to add some noise. Okay, so that is the beauty of the EV. So this is the different types of electric machines we have in the literature. So, but nowadays the majority of the OEMs are using either induction motor or permanent magnet synchronous motor or switched reluctance motors. So these are the three different motors we have in the electric vehicle application. Of course, some DC series motor also being utilized in particular vehicles, but because of the huge maintenance required for the DC motors, very less industries are going for DC motors. Otherwise, most of the industries are going for the either induction, PMSM, and then switched reluctance. So PMSM is giving the high torque density, and the wherever if you need a quicker pickup, then such kind of machines are going for the PMSM motors. So here you can see the characteristics of each motors, that is DC motor, induction motor, PMSM motor. So in all aspect, majority aspect, if you see not only the cost, other aspect. So in terms of the cost, the PMSM is the more, but other like power density, it is having a high power density PMSM motor, and efficiency also it will be given more than 95%, and the controllability also good, and then reliability also good. So this is the certain advantage we were having with the PMSM motor, and there are certain advantages with the induction motor, like reliability is more compared to the PMSM motor. And which models are using this EV electric motors are being utilized by the OEM, the manufacturer. So this is G-Van is using separate excited DC motor. As I said, only few companies are using this DC motor, and then others are using Honda EV Plus using PMSM motor, and then other EVs like Tata Nexon, they are using the PMSM motor in their application, EV application. Hyundai also they are using the PMSM, and the MG EV also they are using PMSM. But Tata Tigor they are using induction motor. Okay, so based on their pickup, based on the application, they are taking the motors. Okay, so and then we need to have a particular controller to control the motors. So we will have a different speed control methods in the literature. So we will discuss what are the types of speed control methods we will have it to control the AC motors. That is AC drives we can call induction motor or PMSM motor or SRM motors. So in the literature, we have different types of controllers. The first one is the scalar control. The in the initial days, we were utilizing the scalar control concept because it is the beauty. But the problem with the scalar control method is that we can able to control the frequency and the magnitude of a vector, that may be a voltage, current, or flux. But we unable to control their instantaneous positions. Okay, so that is the disadvantage of scalar control. You can see the more clearly in this images, the phasor diagram. So here we can control the magnitude and frequency positions. But by using the vector control concept, not only the magnitude and the direction, we can also control their instantaneous position. That's why people are using the vector control concept in their drive applications. And then why the vector control method? So basically, before 20th century, so DC motors, the most of the industries are using the DC motor. What is the reason? Because the DC motors are the best controllers. In what terms? So this is the separate excited DC motor. So here, if you give a separate means DC power, separate DC power to the field winding, if they excite the field, and then here, if you provide the separate DC supply, then it drives the armature current. By keeping this flux constant, we can vary the IA. It means we can control the torque of the machine independent from the flux. We know the torque equation of any generalized torque equation of a machines, electrical machines. The torque is directly proportional to kd of psi f or psi k, or Ia multiplied with Ia. So for the DC motor, the armature current is orthogonal to the field flux control. It means we are controlling armature current independently from the field current. So this is the beauty of the DC motor. We can control the torque of the machine easily, and this is the best motors to in terms of the control aspect. But because of these brushes and the commutators, always maintenance is required. Due to these reasons, the industries are moving to the AC motors. Then, so here, how can we utilize the AC motors, and how can we get the what are the advantages there in the DC motor? The same advantage, how can we achieve for in case of the AC motors? Basically, if you see the electromagnetic torque equation of a AC motor, so here I have taken a induction motor. So in case of the induction motor, we have a stator quantities, rotor quantities, and then the angle between the stator and the rotor. So this is the seventh order equation. To this equation. If you see this equation, this is the DC motor torque equation. This is the AC motor torque equation. This equation is huge complex. Okay. To control this equation, we need to have a large mathematical functions are required. So it is a huge complex. So how can we get the advantage of the DC motors from the AC motors? So if you implement the vector control concept, then the vector control concept will give you the torque equation. Is torque is directly proportional to psi s multiplied with is or psi r multiplied with is. So somehow, if you can make the flux linkage with is in a 90 degrees, or the rotor flux linkage with the stator current in a 90 degrees, then in that aspect you can imagine that the induction motor is behaving like a DC motor. So how can we make this mathematical equation into this equation? So by using the vector control concept, we can make that happen. So by using this vector control method, we can operate this induction motor like a DC motor, so that we can control the torque independently from the flux. IQS is the torque component, IDS is the flux component. So both the phasor diagram you can see, both are similar. IA is the torque component, IF is the field component. This is DC and this is the AC. So that is the beauty of the vector control concept. And the same thing which I have said recently. So either in this mathematical expression or in this way, that is in between the stator flux linkage or rotor flux linkage with respect to the IS. If we can make the angle between these two is 90 degrees, then imagine that at that condition that AC motor is operating like a DC motor. And then what are the different types of vector controls we were having in the literature? So in the literature we have different types of controllers. That is, first one is the field oriented control method, and then director control method, director control with space vector modulation, and then model predictive control methods. So these are the different methods are available. So why these methods are coming, means why the people have invented these types of methods, why they are not satisfied with the FOC? Because the field oriented control method has certain drawbacks. What are the drawbacks of the field oriented control method? So we will see from the upcoming slides. Okay. So initial days the FOC was implemented. Then because of the certain drawbacks in the FOC, people have researchers have implemented the director control method. Then researchers have found the certain drawbacks in the director control method. Then they, in order to reduce the drawbacks, people went for the DTC with space vector modulation, and then the advanced control methods like model PT control methods. Now, basically, the model PT control methods are utilizing in a process industry like chemical industries because they need to process continuously. So these model PT controllers are using in the process industry basically. But nowadays people are adapting this model PT controller into the, means the MPC is not only limited to the process industry nowadays. It is being adopted by the electrical engineers, mechanical engineers, the computer science engineers. The model PT controllers is only the requirement is the it need to have a model. Okay, it need to have a state space model. If you have a state space model, then we can utilize the model predictive concept in any of these applications. So nowadays we are usually utilizing this model predictive controller for the drive application, and this is the one of the advanced method for compared to FOC and the DTC extent. So what is the advantage we will get? We will see the end of this section. So if you see if you understand the FOC and the DTC, then only you can understand the MPC, what advantage we are getting from the MPC. So the same thing, we are implementing a closed loop controller. So basically the drive, we need to have a closed loop to get the better torque and flux profile. Okay. So, okay, 5 minutes please.
So, dear participants, let us have a tea break of 5 minutes. Counselors.
ఇక్కడ వాయిస్ ని మ్యూట్ చేయడం ఉండదా? లైవ్ ఓకే, వాయిస్ గుడ్. అదే మేడం చెప్పారు. అదే నేను చెప్పాను కదా, నేను మా ఇంటి నుంచి ఇప్పుడు సో అన్న యావరేజ్ నేను ఒక 15 to 16 కిలోమీటర్స్ ఉంటాను. సో 15 to 16 కిలోమీటర్స్ ఇది దాన్ని స్పెండ్ చేస్తే కండి రిటర్న్ ఎక్కువ పడాలి. స్పెండ్ చేసేది కంటే మనం ఇన్వెస్ట్ చేసేది ఎక్కువ. 5 years తర్వాత బ్యాటరీ really. Hmm. Okay. You just send me an email. No problem. You just send an email to the purchase section and like we were searching for the price of this item. Kindly give us a few more days time, 1 week of it, so that we will explain. Have you received any amount? Today I'm outside, so tomorrow I will. I don't know these days why the more deals are happening. Okay. associate professor ulla. నాకు associate ఇది అడ్వాన్స్ కదా మీరు అప్లై ఎందుకంటే నా ఫ్రెండే ఉన్నాడు అతను అలానే ఛార్జింగ్ పడదు మేబీ 6 to 7 minutes అవుతుంది ఫుల్ ఛార్జింగ్ 7 minutes ఫాస్ట్ వెళ్తాం ఈ రూపీస్ అదే 50 kilometers తిరగడానికి ఇయర్కి 15 to 16 crores per day అవుతుంది ఆల్మోస్ట్ 3 acres సో 4 acres సో 400 plus వాళ్ళకి వాళ్ళతో మాట్లాడితే తెలుస్తుంది ఫేస్ అయితే వాళ్ళు ఏదైతే పెట్టినా మార్నింగ్ అదే గెయిన్ అవుతున్నాడు అంటే అదే మోర్ దెన్ సర్టన్ కిలోమీటర్స్ వరకు అడ్వాంటేజ్ Okay, participants, we will see now different speed control of induction motor or EMS motor. We can call it as AC motors. So here we have taken initially induction motor. Then we have found the limitations of induction motor, like its torque density is less compared to the AC EMS motor. So majority of the OEMs are considering in heavy application the PMS motor. So we started doing research in the PMS motor instead of the induction motor. But after 5 PhD scholars, 2 are working on the induction motor and 3 are working on the PMS motor, and 3-phase PMS motor, and then the multi-phase PMS motor, and then the multi-phase, that is 5-phase induction motor. So in the both the motors, people, scholars are working, and I'll show you the slides. What advantage we are getting from the PMS and induction motor. So these are the different control methods are available in the literature, and basically the I have done most of the all the control methods. Means the field rate control methods I have implemented, director control methods and director control method with space vector modulation, and then we went to the model PT controllers, and then advanced methods like modified model PT controllers and torque controllers we have implemented, and then in the converter parts. So for any controllers, we need to have a converter parts, that is the inverter. So we have utilized 2 levels, 3 levels, and 5 levels. Each level having its own advantage and disadvantage. We will cover all those things. And then the motors, we have done induction motor and the EMS motors, and we started doing the BLDC motors, but it is limited to the solar water pumping system, because real DC motor having certain restrictions that more than the 10 kilowatt or 15 kilowatt, we will not prefer the BLDC motors. So it has its constructional drawbacks, due to which the BLDC motors are limited to the three wheelers and then certain low applications like fans and etc. And we majorly concentrating on four wheelers and then public transportation and traction applications. So for that application, we are considering the induction motor and then EMSL motors. Okay. So and then the feedback we are measuring through the encoders are tachogenerators basically. So those are the sensors, but which create certain drawbacks, like we need to spend some amount on the sensors, that is encoders and the tachogenerators. So that is the one thing. The another disadvantage we get from the sensors, that if some obstacle comes between the sensor, the speed sensor and the shaft, then we will not get the accurate speed, actual speed response, because we are comparing the measured speed with the reference speed. So when we are comparing, so if we don't sense the actual value of the shaft, then we will get the error speed is huge. Basically, the error speed is measured, means calculated from the reference speed minus the measured speed. Then we will get the error will be huge. So we need to have a proper sensing. So if some obstacle is there, then the sensor will not give. So in that case, our controller fails. Means the desired output which we want, means the proper torque output and the flux, less simple flux we need. So those things we will not get. So to avoid those conditions, people are going for the speed estimation instead of the speed measuring. Okay, so how can we measure the speed? So today topic we were having the afternoon session. How can we measure the speed? Means we can, how can we estimate the speed using different types of methods are available in the literature. Okay, so this is the speed estimation we were having in the feedback. So the first controller in the vector control concept is that the field oriented control method. So in this field oriented control, this is the basically the schematic diagram. How can we implement the field oriented control method? So these are the terminals from the machine side, and this is the control side part. So we will see more deeply in the diagram. So in the field oriented control method, there are two types are available. The first type is the indirect field oriented control. So indirect rotor flux orientation we can call it as. So what is indirect? The name itself is saying we are making the flux orientation, the rotor flux orientation indirect. It means we are predicting, we are estimating the angle of the theta indirectly by taking the support of the slip speed. So because of this slip speed calculation, the we are predicting the orientation angle theta indirectly. So, how is there any method we have with that? Can we estimate the theta directly from the measured quantities? Yes, we have another method that is called as a direct rotor flux orientation control method. By using that method, we can calculate the theta directly. But while implementation, we used to get the more advantage from the indirect rotor flux orientation, because we are getting the less ripple conflict from the this method, because we are adding the slip speed with the actual speed. So this is that method, and this is from this side we call it as a rotating frame, and this side is we are having the stationary frame, because this is the inverse path transformation. This is converting from the rotating reference frame to the stationary quantities we will get, and means transportation, that is the inverse path transformation we have. and this is the inverse clock transformation. That inverse clock transformation again, the two stationary quantities are converted into the three stationary quantities that will be fed to the PWM modulator. And this is the scheme, we call it as a indirect rotor flux field rate control scheme. Why this indirect is coming means because the actual speed is added with the slip speed and the theta is calculated with the help of the omega slip. And this is the equations how we are replacing for the transformation. And this is the direct rotor flux. So again in the direct rotor flux, so here the orientation angle theta is calculated directly by with the support of the measured quantities. What are the measured quantities? We are measuring the voltages and then currents. So we are measuring the stator current and then voltages by using voltage sensor and then current sensor. So these quantities, with the support of this voltage and current quantities, we can calculate the sides. Sides is equal to integral of VDS minus IDS RS. So that we can calculate sides easily. Sides easily by using the this measured quantities. And the theta is equal to tan inverse of sides by sides. So we can calculate the theta directly. So rotor flux we are calculating. So the rotor quantities we can take it. So this is the, by using the mathematical equation only we are calculating the theta easily. That's why the name, we are calculating the rotor flux orientation with the support of the measured quantities directly. We are not utilizing any slip speed in this method. So here we are calculating the side S and side S by using the measured quantities, voltage and currents. But instead of using this voltage and current, there is another way. If you can keep the two flux sensors orthogonal to each other, like 90 degrees angle, one sensor is here and another sensor is here. One sensor will be sense the side gears and the other sensor will sense the position of side gears. Means rotor quantities, torque quantities and the flux quantities we can take it as. So here the side gears and the side gears can be converted into the side year and side year by using the mathematical expression, and the theta can be calculated and also side years by side years or side UR by side DR. Okay, so here this is the another method in the direct rotor flux itself. But which method is more feasible? The method which is there here, that is we by calculating the theta with the support of the voltage and current measured quantities, because we are using those voltage sensor and the current sensor outside of the motor. We are placing the current sensor in series with the base, and in between the voltage sensor in between the two lines are the line to ground, which are connected outside. But the flux sensor we need to keep in the machine, inside the machine. If we keep the flux sensor inside the machine will vibrate while running. So when it will vibrate, there is a chance of falling on the rotor. Thereby, it damages the machine. So the second method in the direct rotor flux by using the flux sensor is the harmful one. That's why people are using only this method by measuring the voltage current quantities outside. So this is that method I have said. So two flux sensors are using, then directly they are sensing the flux and they are calculating the. This method is not that much reliable. So here we can apply the field within method to operate over a wide speed range. We can the flux, thereby we can get the more than the rated speed of the drive. So this is the in the same single picture we have shown the indirect field control method and the direct field control method. So this is the portion is changing for the indirect and the direct field. And here why we need to consider the different types of motors. So here the permanent magnet motor having a certain advantage like having a high torque density. So you can see the torque density of the BMS motor is 28,860, and then induction motor 4,170, and the switch reactor motor is having 6,780. So this is the reason the permanent magnet motors having the high torque density, and it provides the high efficiency compared to the induction motors. And then certain other advantages also. And then we have simulated first before going for the experimental validation. We need to have a simulation results so that we can compare the side by side. So by using the mathematical modeling of the PMS motor, we have designed the simulation, and then we have compared with the hardware. So here we need to have a target electromagnetic torque equation. So constructional wise, the PMS motor has two types. It's only based on the construction, integral type and then surface mounted permanent magnet synchronous motor. So the torque equation varies depends upon the type of the motor. So this is the equation applicable for the this interior type permanent magnet synchronous motor. This is the torque equation. So if you want to take the surface mounted PMS motor, then here this fellow changes. So in case of the surface mounted, the LD is equal to LQ, LQ is equal to the LS. So this fellow will be 0, and the final torque expression, the electromagnetic torque expression for the surface type motor will be the psi f multiplied with I. So based on the type of the motor, torque equation will be varies. That's why we have given for both the type. And we have taken the surface mounted, and this is the result for the surface mounted under no load condition and then loaded condition. Why? Because in our laboratory we have surface mounted PMS motor, we don't have interior permanent magnet synchronous motor. Because while comparing, we need to have a same specification, same result we need to compare side by side for the experimental and the simulation. So now the other method we have in the lecture is that the direct torque control method. So why people are going for the direct torque control method when they are already having the field oriented control method? So if you see the here on the hand. So in the field oriented control method, this if you see this diagram, it's a very complex. It's having the lots of parts, like it requires the clock transformation, path transformation, inverse path transformation, and then PW modulators also required. And then these are the inner current controllers, and then sleep calculation. Everything means the all together it makes a huge complex. That is the first drawback. And then second drawback, to calculate the slip speed, you need to have a mathematical equation. So that mathematical equation has the motor parameters of RS, RR. So the RR and RS is the sensitive parameters. Like if a motor operates throughout the day, then the parameter varies. Means the stator resistance and the rotor resistance varies. If you operate entire day. So if parameters varies, then the output which we require the accurate result we will not get it, because it changes the parameter values. So this method is the parameter dependency. This is the second disadvantage. And this method requires the huge number of controllers. That is outside speed controller, inside current controllers. So the controllers we have taken like a PI controllers. So these PI controllers require a tuning. So these tunings kpk values we need to tune. So for a particular speed, the kpk values will be the changes. So if you change the speed, reference speed, then kpk values also changes. So these kpk values we need to tune in different conditions, because it will not remain same for all the conditions. That is the drawback of the PI controller. So to avoid certain drawbacks of the this field oriented control method, researchers gone for the direct torque control method. So now in the 1980s, the fellow top associate development group has implemented this direct current control method. So you can see the schematic diagram of the direct current control method. So here you can see the number of blocks are very less compared to the field oriented control method. This is the one of the advantage, and here this method does not require any PWM modulator. Okay, so whatever the voltage vector being selected by this flux controller and torque controller, so the direct voltage vector is applied to the on the power electronics converters. Okay, suppose from this block, that is voltage vector selection table, we will get a voltage vector V1. V1 means 1 0 0. So in two level inverter, we will have a any level of inverter. It is a three phase machine, so three legs we will have. So 1 0 0 means the first leg of the upper switch, the remaining two legs of the lower switch will be on. So in this method we don't require any PW modulator at all. But in case of the field oriented control method, we need to have a different PW modulator along with the control method. Okay, this is the one of the advantage, and the second advantage is that we this method don't require any inner PI controller. Only one speed controller is there, so only one PI controller is sufficient for this method. Thereby, we can tune only this KPK values. The inner current controller, inner PI controllers we don't have. So thereby, we can reduce the complexity of the system. So this is the advantage of this method. So these are the two advantages of this method. So how we are implementing the direct torque control method? So basically the name itself is saying we are controlling the torque directly. So how we are controlling the torque directly? Basically we need to see this equation. So S is equal to integral of Vs minus Vs minus Vs minus Is Rs of Vt. So here if you see this equation carefully, so for a smaller interval of time, imagine that the stator resistance will be, the voltage drop at resistance is 0. So when you consider the stator resistance drop is 0, then Is is directly proportional to Vs, that is integral of. Or we can write Vs is equal to d by dt of psi s, or change in psi s is equal to Vs of dt. So remember this equation. So we need to remember this equation while implementing the direct torque control method. So here, this is the equation we need to remember. The change in psi s is equal to Vs of change in time. And we know that the electromagnetic torque equation T is equal to some constant psi r and psi s and sin of gamma. The gamma will be the angle between the rotor flux and then stator flux. So now, how the direct means how we are controlling the torque directly by using the direct torque control method, we will see from this phasor diagram. So here in a particular sampling time, imagine that we will have a the stator flux linkage magnet is the red line, and then the rotor flux linkage will be the this line. So the angle between the stator flux and the rotor flux will be the gamma. So the gamma will be the angle between stator flux and then rotor flux. So now for a smaller interval of time, imagine that we have applied a voltage vector Vs. So here voltage vector Vs we have applied. So now this what is the Vs? Vs is the voltage vector, that is the switching states of a power trans converter, that is a inverter. So two level inverter we have utilized. So when you are utilizing the two level inverter, there will be a 8 switching states. 6 are active voltage vector, 2 are null vectors. So depends upon the voltage vector applied, then the position of the stator flux linkage will be changes. Now the psi s is for a small interval of time, the Vs V3 is applied. When V3 is applied, the psi s is changing from this point to this point. So when the psi s is changing, whether psi r is not changing? Yes, of course, psi r also changes, but the ratio between the psi s and psi r will be huge, because whenever we are changing the stator voltage, initially the stator flux linkages act immediately, then it passes through the air gap, and then it will generate the EMF, thereby current will be flow through the EMF, then the flux, rotor flux linkage will be generated. It will take certain time. So, but what we are applying? We are applying the voltage vector for a smaller interval of time. For a smaller when we are applying for the smaller interval of time, we are imagining the rotor flux will be remain constant. When the rotor flux is remain constant, the psi s is changing from this point to this point, and then the angle between psi s and psi r is increasing. The earlier angle will be this one, and then the current angle will be this one. So angle between psi s and psi r is changing. So when the angle changes, then what we know the equation? The electromagnetic torque equation is directly proportional to psi s, psi r, sin gamma. When the gamma value is increasing, then the electromagnetic torque is increasing when we are applying a particular voltage. So what we understood here? So whenever we are applying a particular voltage vector, we are directly controlling the electromagnetic torque. So that is the beauty of this method. We are controlling the torque directly by applying a particular voltage vector. So this is in particular case. So this, as I said, we are using the two-level voltage source inverter, and in this we will have 8 switching states are possible. 6 are active and 2 are the null. And here we will write a logic based on the input receiving from the flux controller, that is flux hysteresis controller, and then torque hysteresis controller. So here how we will write a logic. So here that logic we will write from this phasor diagram. So here the phasor diagram, let's imagine that we are in there are 6 sectors. Each sector is displaced by the 60 degrees. So 6 sectors, 6 just 360 degrees. So now we are in a sector 1. In the sector 1, we are applying the voltage vector, that is switching states we are applying. So for a smaller interval of time, we are applying the voltage vector. When we are applying voltage vector V2, what is the response of the torque? Means whether torque is increasing or decreasing, flux is increasing or decreasing. So now carefully see the phasor diagram. So initially, for a small interval of time, voltage vector V2 is applied. So before applying the voltage vector V2, the stator flux linkage magnitude psi s is the red line, and then the rotor flux linkage will be the green line. So angle between the stator flux and the rotor flux will be the gamma. Now for the smaller interval of time, the voltage vector V2 is applied. When V2 is applied, then the psi s is changing from this point to this point. So you can see this is the V2. So now the rotor flux linkage will be constant because of this large time constant, and the angle between psi s and psi r is increasing. So whenever we are applying voltage vector V2, the angle between psi s and psi r is increasing, thereby torque is increasing. So that is the torque is increasing. Now coming to the flux point. So now earlier magnitude of the stator flux linkage is this is the earlier magnitude, and after applying voltage vector V2, the current magnitude of the V2 will be this is the point. So now you see the magnitude of the flux linkage, earlier magnitude will be this much, and the current magnitude is increased from this point to this point. It means whenever we are applying voltage vector V2, the flux magnitude is increased. So during the voltage vector V2 is applied, so both torque and flux is increasing. So from this phasor diagram, we are easily understanding how we are controlling the torque and flux when we are applied the voltage vector V2. Then what about the voltage vector V3 is applied? So torque is again increasing, but what about the flux? So initial value of the flux magnitude is red line. After V3 is applied, the current magnitude of the flux will be this is the current magnitude. It means the magnitude is decreasing. So the magnitude of the flux is decreasing when we have applied the voltage vector V. Similarly, V4. So when we have applied V5, angle reduces and then magnitude of the flux also reduces. So in when we apply V5, both torque and flux reduces. Likewise, we will write a logic. So this is the that logic. So in all 360 degrees, we will write a logic what will be happen for the next interval of the time. So this is that trajectory, and based on the applying of the voltage vector, the switches will be on and off. Thereby, we can control the motor accurately, and we will get the less ripple content in the torque and the flux. So here another part we have in this diagram is motor. So we have considered the PMS motor, and this is the simulation diagram we have simulated in the MATLAB Simulink environment. So we have not taken program because we are working on the drive application. So simulation only we have made. And while making the simulation, there are things are possible. One is the PMSM motor block already available in the Simulink library, and this is the block we have designed by using the mathematical equation. So why? What is the difference? The difference is that if you double click this image, then you cannot see what is there inside. But you can enter the power value, voltage value, current value of this EMS motor. But if you click on this, then we can see entire mathematical equation inside of this motor because you created this one. Okay, so we can see the behavior of the each parameter by opening the each parameter. We can track the graph of the each parameter inside of this motor. But here we cannot track. We can track only the torque, speed, and currents of the motor only. But we can see each and every parameter in that. So if you ask me, then prefer to go the mathematical expression of the simulation. And this is the equation we have considered for molding, and this is the torque expression I have shown already, and this is that Simulink diagram we have designed by using the mathematical equation, and this by using the mathematical equation only we created the Simulink, and this is the adaptive models of estimating the flux, torque, and the angle. Everything is created within the mathematical equation. And then another part we have in this schematic diagram is the speed controller. Basically, initially we have given a speed of the imagine 1000 rpm. So now at the time of 1000 rpm, we have applied a particular voltage vector and it is fed to the power transistor converter. Okay, so from the motor by using the encoder, that is tacho generator or encoder, we are sensing the actual speed of the motor. So that actual speed of the motor is compared with the reference speed. Then the error speed is fed to the PI controller. So basically it is not a PI controller, it is a speed controller. So speed controller, we have taken PI as a speed controller initially. Okay. So generally most of the people consider a speed controller as the PI controller because it is easy to implement. So the PI controller is reduces the try to reduce the error between the actual speed and the reference speed. Okay, so this is the thing happens in the speed controller. So how can we design the KPK values? So there are different ways to use the KPK values. The first way people generate use the hit and try. So initially they apply the proportional value. Then suppose they have given the 1000 rpm. So by varying the proportional gain value, so they try to get the approximately 1000 rpm. Then they vary the K value to reduce the bandwidth between the 5%. Then they increase the up to the getting the 5%, they increase the K value. So this is the way they generally prefer the KPK value using the hidden trailer method. But we have done by estimating the KPK value by using the root locus method. So by taking the transfer function, closed loop transfer function of a PI controller, we have used the KPK values. So KP value is 1.75 and then rotor time constant will be the 0.059. And so here we need to have a switching logic, and we have created a switching logic. As I said, this is a two level inverter, so there will be 8 switching states: 100, 110, 010. Likewise, there are 8 switching states. So based on the voltage vector is applied, the corresponding switching state will be act. Then that is fed to the directly inverter. So thereby the corresponding switches will be on. And this is the two level inverter schematic diagram, and this is the result. This is the result. So here you can see the transient performance of the under no load condition. It is far better compared to the FOC method. But the drawback of this method is the torque ripple of this method is very high. You can see the current ripples also very high. So thereby we will have a high THD in the current and then voltages. So we need to reduce this torque ripple. Basically, for the EV application, the torque ripple must be less as possible. Because if you are having more ripple, then your vehicle will be vibrate. So the first requirement of any vehicle, we need to reduce the torque ripple. Okay. So to reduce the torque ripple, to operate the machine smoothly, we have implemented the another method, that is the direct torque control method with space vector modulation. So here basically in the direct torque control method, we are utilizing the flux hysteresis and the torque hysteresis controller. So because of it, we were having the variable switching frequency. You can see the pulses. So all the pulses are different magnitudes. But here you can see the this this is the DT is with space vector modulation. So all the pulses with the same magnitude. Okay, so that's why we are getting here the constant switching frequency. Here it is a variable switching frequency. Because of the variable switching frequency only, we are getting the huge ripple content in the direct torque control method. So to avoid this one, we are implementing the space vector modulation. So now if you see this image, so this is the image is comprised of two things. One is the field oriented control method and another one is the direct torque control method. So this is the portion is the part of the direct torque control method, and this is the portion of the field oriented control method. So in the field oriented control method, we need to have a controllers. So again, this is a PI controller, and this is the modulator. So inner PI controller and the modular is required in case of the field oriented control method. So whereas in the direct torque control method, we need to have a estimation. So this method has the advantage, whatever the advantage we are having the direct torque control method. At the same time, whatever the drawbacks of the field oriented control methods are rectified. What is the drawback of the field oriented control method? That is the parameter sensitivity. We don't have any slip speed here. Slip speed is avoided. So thereby the parameter sensitivity is avoided. So whatever the drawback is there in the field oriented control method is avoided with this method. So this is the beauty of this method. So now in this method we need to implement the space vector modulation. So how can we implement the space vector modulation? So the space vector modulation is implemented to estimate the reference voltage vector. So we need to estimate the reference voltage vector. So to estimate this reference voltage vector, we require three neighboring voltage vectors. So we need to estimate this red line V reference. So to estimate this one, we need to have a neighboring three reference voltage vectors. That is two active. V1 is active, V2 active, and V0 is the null vector. So two active vectors are required, one null vector is required to identify the V reference. So how can we identify? To identify this one, we have a certain procedure. So listen this carefully. So we need to have a certain procedure. So we need to calculate the dwell time first. So for calculating the dwell time, initially we need to identify the sector. So we need to identify the sector first. So in this diagram we have 6 sectors: sector 1, sector 2, sector 3, sector 4, 5 and 6. So this V reference can be fallen in any of the sector. So how can we identify this V reference is falling in the particular sector? There may be a chance of falling sector 4 also. So we need to identify initially sector number. After identifying the sector number, the second step we need to make, that is identifying a region. So in which region the V reference is falling? This is the triangular region. It is having only one region because this is the 2-level inverter. If you go for the 3-level inverter, then there may be a chance of having multiple regions. That is n minus 1 square. Region decided based on the n minus 1 square. N is the level. 3 minus 1 square means 2 power 2. There will be in the particular sector there are 4 regions exist. But here we have only one because we need not to calculate the region number because of 2-level inverter. But if you go for the 3-level inverter, after identifying a sector number, we need to identify the region also. Okay, then only we can calculate the dwell times for the switch pulse generation. Okay, so first job is identifying a sector. So how can we identify a sector? So we can identify a sector by using this mathematical expression. So remember this mathematical expression, the same expression we will utilize for the irrespective of the level. So K is equal to fix of theta by 60 plus 1. So here why we are using this fixed term? Because we are having sector 1, sector 2, sector 3, sector 4. All are integer values. We don't have any non-integer values. So to get the integer value, we are using the fixed term. This is a MATLAB arithmetic function which avoid the non-integer values. So now after applying this mathematical equation, imagine that the V reference has been fallen in the sector 1. It means this red line has fallen in the sector 1. So after identifying the sector, then what is our second job? We need to identify the region. Okay, that is triangular region. So in the sector 1, we have only one triangular region. So need not to identify the region number because this is 2-level inverter. We have only one triangular region. So imagine that we found the region also. Okay. Then third job is that, what is the third job? Third job is to calculate the dwell times of TA, TB, TC. So to calculate the dwell times, so now the V reference is fallen in this region. So what are the nearest voltage vector? To realize the reference voltage vector, we need to have 3 vectors, 2 active vectors, nearest active vectors and 1 null vector. So which are the nearest to the V reference? V1 is the near, V2 is the near, V0 is the near. This V6 is the far away, V3 is the far away. So after identifying the region and the sector, we need to identify which are the voltage vector nearer to the V reference. Once you identify those active vector and the null vector, by utilizing their magnitudes, we can calculate the dwell times. So V reference is fallen in the sector 1 of the region this one, and the nearest voltage vector of this V reference is V1, V2, V0. Now what is the V1? The V1 is equal to, this maximum magnitude of the V1 will be 2 by 3 VDC, 2 by 3 VDC e power j theta. So this is the x-axis. So this is the x-axis for the, to the V reference. This is the x-axis. The angle will be 0. So e power j 0. So we can have a magnitude of the V1 that is equal to 2 by 3 VDC is the magnitude. Then what about the magnitude of the V2? The V2 is 60 degrees phase displacement from the V1. So here V2 is equal to 2 by 3 VDC e power j 60. Then we can write in terms of the complex equation. Then we can get the V2. So that you can see here. So here, what is V2? V2 is equal to 2 by 3 VDC cos 60 plus J sin 60. And V1 is equal to 2 by 3 VDC because cos 0 will be 1. Okay. So we will have a V1 magnitude, V2 magnitude and V0 also. So here, for a particular sampling time Ts, we are calculating the V reference, that is V reference is equal to, we have nearest voltage vectors are V1, V2, V0. So V reference is equal to V1 plus V2 plus V0. So the total sampling time is Ts. Now the point is how long we are applying V1. So we are applying V1 for the duration of T1. We are applying V2 for the duration of T2. We are applying V0 for the duration of T0. So the volt second balancing equation, by taking the help of the volt second balancing equation, we can write V reference Ts is equal to V1 T1 plus V2 T2 plus V0 T0. So what is the total sampling time? That is the time which will be applied for the duration of V1, V2, V0, T1 plus T2 plus T0. So now we know the magnitude of the V1, V2 and the V0. Substitute the equation number 3 into the equation number 1 and then separate the real and the imaginary part. The equation number 4 is the real one, equation number 5 is the imaginary one. Now carefully observe the equation number 4 and the equation number 5. So we are calculating the dwell time. So in the equation number 4 we have a T1, T2 are the unknown. In the equation number 5 only T2 is the unknown. So from the equation number 5, first get the T2. So we identify the dwell time T2. Then T2 is substituted in the equation number 4. Thereby we can identify the T1. So we know the total sampling time. From this equation 4 and 5 we found T2 and the T1. Can't we find the T0? Because Ts minus T1 minus T2 we can find the T0. So now we found the dwell time of T1, T2 and the T0. So here this is the T1, this is T2, this is the T0. So we calculated the dwell time when the sector is falling in the sector, when the voltage reference is falling in the sector. But what about if it is fallen here? If it is fallen here, do we need to make all the mathematical expression again and again? Need not to make it. So in the dwell time T1, wherever you find the theta, in the dwell time T2, wherever you find the theta, you replace this theta with theta dash. The theta dash is equal to theta minus r k minus 1 r 5 by 3. So that we can identify the dwell times in any of the sector. So thereby we can design the switching pulses. So while designing the switching pulses, we need to take the certain conditions. What are those conditions? So here this is the inverter. In the inverter we have 3 legs. So the first condition is that when the voltage vector falls in a particular sector, all the 3 legs must be on, either upper switches or lower switches. So that is the first case. The second case is that when the voltage reference is moving from one sector to another sector, from one sector to another sector, the transition in a switch means on and off in a off of the switch must be minimum 1 or 0. To avoid the ripple contents of the torque and flux, this condition must be implemented. So, so thereby we can design these beautiful pulses for all the sectors. And now, after identifying the pulses, basically we have flux controller, torque controller, and the speed controller. So these are utilized the PI controller here. So we need to choose the PI controller for flux, torque, and then speed. So how can we use? There are different methods. Different errors also we can utilize. And here we have used the root locus method because we have a transfer function. So by using the closed loop transfer function, we have designed the KPK values for the speed controller and the KPK value for the flux controller and the torque controller. So these are those values for the PI controllers of the torque, flux, and the speed control. And this is a simulation diagram. And the mathematical, parameter values of the motor we have considered same parameter value of the experimental setup, because when we are comparing the simulation result with the experimental result side by side, the parameter value must be same for the both the cases. And this is the simulation result of DTC displacement of modulation using two level inverter and under loading condition. And here is the THD. So while implementing, we got the current THD is 10 and the voltage THD is 44. So basically, as per the IEEE standard, the current THD we have got using the direct arc control method is very high. So we have applied the multi-level inverter to reduce the voltage THD and the current THD, because by applying the multi-level inverter, we can have a less ripple content in the current, and we can have a voltage profile similar to the sinusoidal. So this is not the sinusoidal one because of two level inverter. So this is a line voltage. We were having the 4 voltages. So this is the comparison FOC, DTC, and DTC system. Whatever drawbacks are available in these two methods, DTC system can be avoided using DTC system. And then now the point is why we have gone for the 3 level inverter. Why we have gone for the 3 level inverter? Because we were having, first thing is torque ripple contents are more still in the DTC system. Because of that, we were having the current THD is 10, voltage THD is 44. Basically, we will prefer current THD less than the 5%. So voltage we will not consider much. So for that reason, we have gone for the multi-level inverter concept. This, if you see this diagram, only this part is changing because here we are applying the 3-level inverter. So here also we are applying the multi-level inverter. What is the advantage of multi-level inverter? We all know that is we will get the lower profile of the distortion and the lower dV by dt, and we will get the sinusoidal output voltage, and then low THD, current THD, and the voltage, etc., etc. So these are the we have applied in the literature. Basically, three types of the topologies are available. One is the cascade edge switch, another one is the neutral camper point type, and third one is the flying capacitor. So each method having its own advantage and disadvantage. The first method, that is the cascade edge switch. The cascade edge switch gives the better performance, but it is a little bit costlier. Why it is costlier and complexity? Because the each edge bridge required isolated DC sources. Because of the isolated DC source, it increases the cost. At the same time, it increases the complexity. But it gives the better performance because it gives the isolated sources are connected to the capacitor. So the capacitor unbalancing will not occur in case of cascade distribution. So the second thing is, to avoid that drawback, there is another method, that is neutral point clamped inverter or diode clamped inverter. So in the diode clamped inverter, we will have a single DC source which can be applied across the multiple inverters, multiple level inverters. But what is the drawback? So we unable to apply more than 3 or 5 level, because we are applying the particular DC source across the multiple level inverter. So there are capacitors, multiple capacitors are connected. So here these two capacitors are connected across the DC source. So the unbalancing of the capacitor may arise when we apply more than 3 or more than 5 level. So this common mode voltage problem will arise when we apply more than 5 level inverter. Okay, so this is the drawback of the neutral point clamped inverter. So because of this reason, in the literature we hardly find more than the 5 level inverter. So we need to control the common mode voltage. So the common mode voltage may arise, means capacitor voltage will be unbalanced. Okay, so there are certain logic we need to apply which makes the system more complex. So we have not applied more than the 5 level as of today. Maybe in future we will see it. So this problem will not occur in case of the castrated distribution. Okay. So here to avoid the isolated DC sources, we have taken the 3 level diode clamped inverter. And third of all, we have flying capacitors. So different types of capacitors are available for the same level. So again, there also unbalancing of the capacitor voltage occurs. That's why you will not majorly you will find the for the drive application you will find the very less papers on the flying capacitor type methods. So majority of the people are considering this diode clamper because of it has its own advantage because of single isolated DC source is sufficient. Now, the as name suggests 3 level diode clamped inverter, we will have a 3 pole voltages 0.5 VDC, 0, minus 0.5 VDC. So, based on the switching states, there are 4 switches in a particular leg. So, based on the switching states, we will have a 3 pole voltages. And so here also we have applied the space vector modulation to get the proper switching pulses. Thereby, we can reduce the torque ripple and flux ripple. So we are in a demand of flux and torque ripple content reduction. So thereby, we can have a smoother performance of the drive. Thereby, we will have a less vibration in the vehicle. So here we are applying the space vector modulation again. So how can we apply? So to apply the space vector modulation, this step we need to follow. The first step is we need to identify the sector number. So there are 6 sectors. In which sector V reference is fallen, whether it is in fallen 1 or 6. So first we need to identify that. After identifying the sector number, second is the region number. So there are 4 triangular regions exist in this sector 1. So this is the portion of the sector 1. We will identify the region based on this equation n minus 1 square. So 4 regions exist while applying the 3 level inverter. So now thing is that the V reference is fallen in the sector 1, but in which region? So after identifying the sector, we need to identify the region also. After identifying region only, we can say the nearest voltage vectors are this one, this one, this one is the near. Or this one is near in case of here. So we need to identify the region also. Then only we can have a clear idea which one is the nearer to the that V reference. So let's have identify first sector number. That is sector number equation is the same. This is the K is equal to fix of theta by 60 plus 1. So from this equation we will have a imagine that the V reference is falling in the sector 1. So you may think that why you are taking always in the sector 1. So we have taken some imagination. That's it. So you can imagine it is falling in the sector 3 also. Okay. So by using the mathematical equation, in any sector you can take it. Okay. So initially we calculated by thinking in the sector 1. Okay. So now we have considered in the sector 1, and after considering the sector 1, we need to identify the region number. So to identify the region number, what we have taken? We have splitted this V reference. This component V reference is splitted into the 2 components, the K1 and the K2. So now this V reference has been splitted into the K1 and the K2. So what is K1 component and what is K2 component? We have taken a mathematical expression of the K1 is equal to V reference of cos alpha minus 1 by root 3 of sin alpha. So how we arrive this one? But there is a one-page mathematical expression derivation is required to arrive this K1. Okay, if you want, I will provide this expression later on. So K1 is equal to V reference of cos alpha minus 1 by root 3 of sin alpha. Then what is K2 component? K2 is equal to 2 by root 3 of V reference sin alpha. So after splitting V reference, we have 2 components K1 and K2. Now in the sector 1, we have 4 regions. So how can we identify the region? To identify the region, we have certain mathematical equation. We have taken certain mathematical equation. Thereby, that mathematical expression will give us a particular region number. Maybe this one or this one or this one. So, what is that mathematical expression we have considered? So, a condition if k1 is less than 1 by 3, k2 less than 1 by 3, both k1 plus k2 is less than 1 by 3. In that condition, imagine that the V reference is falling in the region 1. If that condition is fulfilled, you imagine that V reference is falling in this case. Or k1 is less than 1 by 3, k2 less than 1 by 3, but both together is greater than 1 by 3. In that case, imagine that the V reference is falling in the region. And third condition we have written, if k1 is greater than 1 by 3, in that case region 3. k2 greater than 1 by 3, in that case region 4. So we need to arrive certain conclusion. So we have to identify the region. How can we identify the region? For that we have written a condition. So that is this condition. So from this condition we got the regions. So delta 1, delta 2, delta 3, delta 4. So now imagine the V reference is falling in the region 1. Okay. So after identifying the region 1, what are the nearest voltage vectors of the region this one? So for this red line, this is the point, V13 is the nearest, V14 is the nearest. V7 is far away, V2 is the far away, V1 is the far away. So now if you see carefully this diagram, if you see carefully this diagram, there are different types of magnitude is available. The maximum magnitude from this point to this point is 2 by 3 VDC. Then what about this magnitude? Then what about this magnitude? This magnitude and this magnitude is different, and this one and this one is the different, and this is the 0. So in this space vector diagram, there are 4 different types of magnitudes are available. Those are this one. So V13 to V18 we call it as small vectors. V7 to V12 we call it as a medium vectors. So this V7 is the medium, V1 is the bigger, and V13 is the small vectors. So likewise we have different vectors and their magnitudes. Okay. So the small vector magnitude is the 0.33. So we can calculate the V13, V14 similar to the 2-level inverter. Okay. What is V13? V13 is equal to 0.333 VDC e power j0. Then e power j0 gives us the cos 0 1. Okay. So V13 can be calculated, V14 calculated. Then substitute this V13, V14 into the volt second balancing equation. Thereby we can calculate the TA and the PV. Okay. So here V13, V14, V0, V reference. All these equations substitute into the volt second balancing equation and separate real and imaginary terms. So this is the real term and this is the imaginary term. So real terms we are having a 2 unknowns, that is TB and the TA. The equation number 7 having only one unknown is the TB. So we can calculate the TB first, substitute 7 into the 6 in place of TB, then we can identify the TA. We know the total sampling time. So the TS minus TA minus TB, thereby we can calculate the T0 also. So now we have calculated the 12 times TA, TB, T0 or TA. In case of when it is falling in the region 1. So what about the region 2, region 3 and region 4? So we can identify those in the different region by substituting wherever you find the alpha, this alpha, you substitute alpha with the alpha dash, then we can identify the other region 12 times. So that is this 12 times. So thereby we can design these beautiful switching pulses for the 3-level inverter, and this is the 3-level inverter. And how, when we apply the 0.5 pole voltage, so upper 2 switches on, and minus 0.5 voltage, lower 2 switches on, and 0 pole voltage, middle switches on. And this is the two level inverter and three level inverter result side by side when we compare. You can see these two results. Here we got the torque profile ripple content is less compared to here. Okay, so this is the beauty of the three level inverter compared to the two level inverter. Of course, when we are going the three level inverter, the complexity of the inverter increases, but we are getting the advantage of ripple content reduction. And this is under loading condition. And this is the current EHD. So here, especially we are going for the three level inverter in two reasons. One is to reduce the torque content, and second one is the to reduce the current EHD and the voltage EHD. So here, in case of three level inverter, we got the current EHD of 3.16. It is less than the 5% as per ITP standard. Here it is 10%. So we are achieved less than the 5%. And we compared under different characteristics. So under loading conditions, settling time of the two level and three level inverter, etc., etc. And we found that the three level inverter is best in all aspects. This is the different conditions. And still there is a certain amount of the torque ripple still exists, and we can further reduce the torque ripple, and current EHD we got around 3.16. So we thought that if we go for the 5 level inverter, maybe further reduction may be possible. Then we have applied and 5 level inverter. So this is the that schematic diagram, and this is the final inverter only changes here and related space vector modulation scheme. And this is diagram of the pi level inverter direct clamped inverter, and these are the switching states. And as per the name suggests, the pi level inverter, there are 5 pole voltage will be there. So those are the 5 pole voltages. And how can we apply a space vector modulation for the pi level inverter? So I'll tell you from this diagram. So earlier we were having a easily suppose V reference is fallen in a particular region. So this is the R line region. So earlier what happens, whenever it is fallen in a particular region, we identify the only single voltage vector nearest to the means. Here one single switching state and single switching state. Single voltage vector is available in nearest to the V reference. It means here one, here one, here one. There are three nearest voltage vectors are possible up to the 3 level. But in the 5 level, see at this point, these are the 3 switching states are possible. At this blue line, there are 2 switching states are possible. At this line, again there are 2 switching states are possible. Or you take this point, this region you take. So when you have the V reference is fallen in this region, the red point there are 4 switching states are there. At this green point, 3 switching states are there. At this green point again 3 switching states are there. Up to the 3 level inverter, we don't have a problem because we have only a single switching state. Single voltage vectors are available. Thereby we have taken easily. But here the problem is that there are 4 voltage vectors are available nearest to this V reference. So which one we need to consider among these 4? Which one we need to consider among these 3? Among these 3. So this is very difficult to identify the nearest voltage vector. So this is the one of the major problem to identify the voltage vector, nearest voltage vector, thereby calculation of the dwell times. So for this reason, we are unable to apply the space vector modulation as it is for the pi level inverter. Then how can we apply? So how can we get the advantage of the pi level inverter? Then we have made small simplicity, like we have simplified the pi level space vector modulation. This is the pi level space vector modulation diagram. So we converted this diagram into the like a this green line, like 2 level inverter. In the we converted 5 level inverter space vector diagram into the 2 level diagram. Thereby we got the beauty of the advantage of the 5 level inverter while implementing like this. Okay, so how we have implemented that one? So we are not different from the steps. We only simplified the 5 level inverter into the 2 level inverter. Okay, so how we have simplified, these are the conditions. The same condition we need to apply. First, identifying of the sector, second is identifying of the region, thereby we will calculate the nearest voltage vectors. So first will be the sector identification. The same mathematical equation we will consider, and imagine that V reference is fallen in the sector 1. After identifying the sector, we need to identify the region. So how can we calculate the region? N minus 1 square. So n minus 1 square. So 5 level inverter. 5 minus 1, 4 square. So 16 regions exist in each sector. So it is little bit difficult because there are 16 regions are exist. But earlier case only 4 regions. Now 16 regions are there. So this is another difficulty if you implement the space vector modulation for 5 level. So to avoid this difficulty, we converted this 5 level space vector modulation into the 2 level base. So for which we have implemented simplified little bit. So consider this way. So let's imagine three slopes, that is root 3 and sorry minus root 3 and the 0, which are passing through the end tip of the V reference. So now this is the V reference. I have considered three slopes, that is this minus root 3 and then 0. So these three slopes are passing through end tip of the V reference. Now we know the beta is equal to, this is the y-axis is the beta, x-axis is the alpha. So this V reference intercepts are beta and alpha. So what is this slope? That is beta is equal to root 3 minus root 3 of alpha minus k1 dash. And this slope having the beta is equal to root 3 of alpha minus k2 dash. And this is the alpha. And so this is the beta is equal to k3 dash. So this is the slope of k3 dash. Now k1 dash, k2 dash, k3 dash we have considered to identify the region and nearest the voltage vectors. So this k1 dash, k2 dash, k3 dash we have considered to identify the region number. Okay. So now to consider the region number, we have the regions of particular number, integer value like 1, 2, 3 up to the 16. We don't have any 1.5, 1.2. So what we have done, this k1 dash, k2 dash, k3 dash, we have scaled to k1, k2, k3. K1 is equal to fix of k1 dash by h. Why we have made it like this? Because we need to identify the region number. To identify the region number, we need to have a nearest voltage vectors. So we have voltage vectors values are integer value. To avoid non-integer value, we consider k1 is equal to fix of k1 dash by h. Then what is h? H is equal to Vm by n minus 1. Okay, so like that for the equation K3 is equal to fix of K3 dash by K. K is equal to 0.866 of Vm by n minus 1. Vm is the maximum magnitude, that is 2 by 3 VDC. Likewise, we found the K1, K2, K3. So to identify the region number, we have taken the help of the K1, K2, K3 and we have written an equation. Delta J is equal to 7 of K1 minus K2, K1 square plus K2 plus K3. Thereby, this equation gives us a single number. So, that number we got it a delta J. So, particular sampling time, the V reference is falling in the reference number, means region number delta J. So, what we have done after identifying this delta J, delta 9, so we have simplified all the 16 regions into the single region. We have considered only single regions. How we consider that one? We have shifted the origin from this point to this point. And the 5 level space vector modulation we converted into the 2 level inverter space vector modulation, and the entire region we consider into the single region. likewise like a two-level inverter. But its corresponding magnitude will be the five-level inverters only. Here basically V2 that is 110. But what is the V2 in the set? That V2 is equal to half H comma K. So we have not differed from the five-level inverter. We have just simplified it into the two-level inverter, but we have taken the values of the five-level inverter only. That is the space vector modulation diagram corresponding values only. Okay, so here V2 is equal to V2 of half H comma K. Here V1 is equal to H comma 0. But in case of two-level inverter, what we are having V1? V1 is equal to 100. Okay, we just simplified the five level space vector diagram into the two level, but we have considered the values of corresponding values only. So thereby we identify the dwell times TA, TB and the TG. So these are the dwell times TA, TB for all the 6 sectors. And we have designed the switching functions for this. And this is the 5 level inverter when we apply the 0.5 voltage, pole voltage and another pole voltage, 0 pole voltage minus 0.25 and 0.5 simulation results under a 2 level inverter, 3 level and 5 level. So you can see the magnitude of the dark ripple content is reduced large compared to 2 and 3. And under loading condition also. And under different as we are applying for the electric vehicle application, so we need to test our algorithm under different over a wide speed range, the low speed, medium speed and high speed also. So we have tested under different conditions, and these are smoothly tracking the different speed conditions. And why we are gone for the 5 level inverter, I have said the reason. So whether our reason means our justification is satisfied. So here you can see the current EHV is 1.68 and the 3 level inverter we have the 3.16. So and the voltage profile you can see. So we are having almost insider voltage profile we got it compared to the 2 level and 3 level inverter. So this is the beauty of the 5 level inverter. So up to 5 level inverter we able to balance the capacitor voltage. So for the, and we able to simplify the space vector modulation. But we found the simplification for the 5 level itself difficulty. That's why we are not gone for the 7 level inverter. So but 7 level inverter we have applied for the cascaded head switch. Okay, because there the capacitor unbalancing problem is not there. And this is the different characteristics and the PhDs under different conditions and result comparison at different cases. So up to now we have seen the field oriented control method, and we have also seen the direct arc control method, and then we have gone for the DTC with space vector modulation. So to reduce the drawback which is available in the corresponding method, we gone for the different methods. So now what is the drawback we have in the DTC space vector modulation? So basically I am showing the drawbacks of the DTC SVM. I could have taken the diagram. So here the drawback, what is the drawback of this DTC space vector? Though we are applying for the 2 level inverter, 3 level and 5 level inverter, thereby we are reducing the top ripple profile and the plus ripple profile, and then current enhancing the THD, current THD and voltage THD. But what is the drawback exists in this method? The drawback exists in this method is the use. Suppose we are operating initially we are operating at 600 RPM. Then we have raised the accelerator. Then it is moving to the 800 RPM, and then 1000 RPM. So the error speed is calculated based on the reference speed minus actual speed, which is measured through the encoder. So we are varying the speed, but are we varying the PI control values? the PI controller values we have given particular value at particular speed. So we are written driver method we are applying. Suppose Kp is 5, Ki is the 2. At what condition? At 600 rpm. Now we move the reference speed into the 800 rpm. So at the time of the 800 rpm, what is the Kpk? Because the transfer function is changing. The transfer function value means the transfer function we are finding based on the parameters of the this parameters values. Okay. Now the V reference is changing from 600 rpm to 800 rpm. At that condition, the kpk values will not be remain the same. The kpk values must be tuned according to the reference value. And the current controller plus controller we are having, tar controller we are having. So these are also using PI controllers. Okay. So when we are using the PI controller again, so here we are having the difficulty of tuning KPK values when the speed is changing. When the speed changes, then here error also changes. Then based on the error, torque error is equal to the reference torque minus measured estimated torque. So this error also changes when the reference speed is changed. Then we need to tune the KPK values corresponding to the omega value. Okay. So this value need to be changed and this value also need to be changed. So the flux is calculated based on the actual speed we receive or the reference speed we set. So all this interlinked with the reference speed which we are setting. So the KPK values we need to tune always whenever we are changing the speed. So this is the drawback we are having with the PI controller. So PI controller values, the KPK values are not changing online based on the reference values of the speed. That is one case. And the second case is we can apply the load on the motor. Maybe sometimes we may apply 30%, 50%, 70%, 80%, or 100%. So whenever we are applying the load, different loads, so during that time also the transformation of the model changes. Thereby this KPK value also changes. But these values are changing. Are we changing online these values? So we are unable to change these values. So this is the very complex. So to avoid this problem, so this internal and that is one problem. And second problem is we need to have a PWM modulator. So we have applied the mathematical equation and we generated the pulses for the means thereby we got the particular voltage vector. So particular voltage vector will switch on the inverters. So this method, DTC with space vector modulation required the inner current control loop. At the same time, PWM modulator also required. So which makes the system complex and which will not give the accurate result whenever the parameter values are changed. Means parameters in the sense the reference quantities are changed. Okay. So how can we avoid this one? We can avoid this one by going for the advanced control method like the model predictive control. The name itself says predicting. So it predicts the next state value in the current state itself. So for better understanding, we will see. So now here we are measuring the actual speed. When we are measuring the actual speed based on the error which we calculated for the previous state. So this is the error. See, this actual speed we received when the torque ripple when the this error torque is so here basically the actual speed we will get based on the input we received for the source voltage source inverter. So it means the previous state value when it means k minus 1 state value when we apply this error, because of this error minimization of the error we got the output. Then we are comparing here. Then error speed is applied to the PI controller. It means the previous state when we have applied the previous state, that is omega r minus 1. So this is the error of the previous state. Based on that we are getting the actual speed. Okay. So, but in the prediction model predictive controller, we are predicting the next stage output, advanced output in the current state itself. That's why the name is saying the model predictive controller. We are predicting the next stage output in the current stage itself, and thereby the model predictive controllers are not required inner current controller and then modulators also. That's why the people are moving to the advanced control method like model predictive controllers, and why it is attracting, because of that reason it is attracting more. The future will be the autonomous vehicles, so driverless vehicles. So the model predictive controller will be acting for the autonomous vehicle, because it need to predict for the next stage based on the what is there any beside vehicle, or what is the distance between the vehicle. So it will be predict the next state value and act accordingly. So the steering will be acted according to the next predicted value. So the MPC model will be applicable for the automobile industry when we are going autonomous vehicles, means electric vehicles. So here the other method we were having the in the vector control concept, that is model predictive controller. So field oriented control method drawback, then we went to the DTC, and the drawback of the DTC is rectified in the DTC SVM, but still it is having the PA controller tuning exists in the DTC SVM, and the modulator also required. So to avoid this one, we are going for the model predictive controller. There we can eliminate the inner current controllers, and also we can avoid the modulators. And now we are going for the model predictive controllers. So I have said the advantage of the model predictive controller. So we are predicting the next state variables in the current state itself. So this is the GIF is showing the results of the PA controller. First, basically we will apply the KP value. So suppose we want a 1500 RPM speed, then we will get the around 1300 RPM by varying the KP value. Then we will vary the K value with the KP value. Then we will get the desired output. So this is the way we will vary the KPK values to get the desired one. Then we can get that one. But will it be reliable? So like we were varying the KP first, then to reduce that band, we are increasing the KI, and to reduce the ripple content, we are increasing the KT. Okay, so we are making this process for a particular speed. So if you want to change the speed again, then this process needs to be followed during the feedback process. So to avoid this problem only, we are going for the predictive controller. So three PI controllers are there, then we need to do for the three different cases. So we are predicting the this GIF is showing the it is predicting the next value in the current state, and it is giving us the desired output. Okay, so if you want the 1500 RPM, then accordingly we give you predict the value. So for the feedback system, it is applicable for the feedback system. And as field control method has different types, similarly the model predictive control methods also has different methods. So here CCS MPC, it is the continuous control set, and this is the finite control set. Okay, so continuous control set and the finite control set. So in the literature you will find the more papers on the finite control set, because like in the FOC we will find the more papers on the indirect field control method, because indirect field control method gives more advantage compared to the DFOC. Similarly, the finite control set gives the more advantage compared to the continuous control sets. Okay, so the MPC method is not limited to a particular application. Earlier days, it is applicable to the processing industries or chemical industries, but now the MPC is being adapted by the various departments like chemical engineering, electrical engineering, mechanical, CSC. So likewise, wherever the states having the mathematical modeling of the state space is applicable, then we can apply the MPC method. So initially we have gone for the finite control set model PT controller. There again we have short origin and the long origin. What is the short origin and what is the long origin? Basically, the drawback of the continuous set model PT controller is that we will not get directly a switching sequence or switching state. We will not get directly. So to get that switching state, we will need to have optimizing the vector. So this is the again a complex problem. That's why we are going for the finite control set method. So here in the finite control set method, again we are having different types of method: short origin, long origin, and then constraint based with weighting factors and without weighting factors and parameter sensitivity. So we will go one by one. So what is the short origin? The short origin is the we are predicting the immediate next state. We are not predicting the multiple states. Okay, so if you see here, now we are here, we are predicting the at the stage of the k. Now we are predicting the k plus 1 instant. We are not predicting the k plus 2 instant. Okay, so we are satisfied with the k plus 1 instant because our systems are compromised. Our systems are having the less computational systems. So high DSPs is required for the going for the long horizon. It means long horizon means I'll show you that diagram also. Uh, so this is the long horizon. We are here. So we are making the more iteration to get the accurate performance. But at what cost? So this kind of system require a high computational systems. Okay, so this may compromise your result. So to get the result, you have to wait 1 day, 2 day, 3 day. Okay, if between power processing there, then again you have to start from the starting. So it will increases the computational burden. Of course, it will give you the accurate result compared to the short horizon. But at what cost? You have to wait for a day. Okay, because it has to go for the longer iteration from here to here, then here. It has to go for the multiple iteration. Then it will give you the accurate performance, for which it will take a time will be more. That's why people are going for the majority people are going for the short horizon, and we can get the maybe not that much accurate, but we are getting near to the accurate result. Thereby, because our systems are compromised, we are having less computational systems, so we need to go for the short horizon only. So this is the difference between the short horizon and the long horizon, and we consider the short horizon for all the cases. And so here in the model PT controller, there are different types of methods available. One is the model predictive current controllers. So what are our constraints? It means whether you want to reduce the current ripples, or you want to reduce the torque ripples, or you want to reduce the flux ripples. So what are your constraints? Based on the constraints, the different methods are available in the literature. So this is the model predictive controllers, current controllers. So their constraints are reducing the current ripples. Another one is the model predictive torque controller. So their constraint is to predict the torque quantities. Then another one is the model predictive flux controller. So their constraint they want to predict the flux values. Another one is the model predictive torque and flux controller. So likewise, the different methods have available in the literature. But every method has its own advantage and disadvantage. Like the model predictive current controller method is don't require any weighting factors, but it has the drawback of the little bit ripple contents. So likewise, each method has its own advantage and the disadvantage. We will see those things. So there are different types of methods are available in the literature. So we have considered the model primitive torque controller with modified one, because this method requires no weighting factors are required. That's why we consider this is the model we designed for our case. And in this method, we need to have the data of IQ, ID, and the reference current of ID and the reference torque TE. We need to have these quantities, and then the estimated values of means the power converter values of switching pulse SA, SB, SC. So to implement the modified model fit torque controller, these five parameters are required. The data of the five parameters is required. So now here also we are implementing 2-level inverter, 3-level inverter, 5-level inverter. So this level of the inverter may change, but the program will be remain same. The iteration may happen multiple times based on the suppose this is 2-level inverter. We were having the 8 possible states. It means I is equal to 1 is to 8, means I is the iterations. Okay, so for the 3-level inverter, we will have a 27 switching states. Possible switching states are 27. It means I is equal to 1 is to 27. And for the 5-level inverter, we will have a 125. How we are getting switching states? Because n power phase. N is the number of level. Phase is the we are having 3 phases. So n is the 2 level, 2 power 3. 2, 2, 2. 2 2 is 4, 4 2 is 8. Similar 3-level inverter. 3 power 3, 3, 3, 3. 3 multiply with 3, 3 multiply with 3. Likewise, 5 level. 5 power 3. 5 multiply with 5, 5 multiply with 5. 25 multiply with 5, 125 switching states. Okay, so the switching states are means the procedure, the flowchart will be the same, but the iteration will be changed. The number of iterations will be changed based on the level of the inverter, but process will be remain same. So, like we have seen the process steps in case of the space vector modulation, the how we have followed for the 2-level, 3-level inverter. For 2-level inverter, initially we identify the sector number, then region number, then nearest voltage vector, then dwell time calculation. The same procedure we followed for the 3-level inverter and the 5-level inverter. Thereby we designed the switching process. So here also there are certain steps. So the same step will need to be followed for the 2-level, 3-level and the 5-level. So what is the first step? We need to identify the finite control set data of input variables. So we need to have a 5 input variables: IDS, IPS, and the TE reference torque and the reference ID, and then switching pulses. So those data are required. So first one is that we need to identify the set data. Then the second step we need to prediction of the variable trajectory. So what are the variable trajectory? Whether your trajectory is the current or the flux or the speed. Then based on that we need to identify the cost function. Okay, so your design will be maybe flux and the error flux or the error torque or error current or something, or you can consider the switching frequency. Okay, so it depends upon the your constraints. So my constraint is the I need to reduce the torque ripple and the flux ripple. So I have considered only error between the torque and the error between the flux. The reference minus the measured one in case of the DDC, but here the reference minus predicted. So what is the difference between the conventional one and then the model PT one is that the error torque we will get from the direct torque control method, the error torque is equal to reference torque minus actual torque, means estimated torque. It means the torque measured in the previous instant. But the model PT control case, what is happening? The error torque is equal to the reference torque minus of the T of K plus 1. It is the next instant, next state output what we get, that is the difference. Okay. So model PT controller will give us the next state variable value. Then we will, this is the one of the important parameter we need to identify the cost function based on the predicted value. Then we will minimize the error. So this is the procedure we need to follow for the 2 level, 3 level and the 5 level inverter. And this is the 2 level inverter. So what is the first procedure? We need to identify the data set. So data set for the 2 level inverter, as I said, n power phase. So the data set for the 2 level inverter will be, there are 8 switching states are available, 1, 2, 3, 4, 5, 6, 7, 8. So we need to create the data sets for the 2 level inverter. Those are the data sets. Then the next point, next step 2 is the predictive modeling of the variables. Which variable you are considering, whether you are considering current or torque or flux. So we need to decide that one. So here equations are not using like it is not supported. Okay, so here we need to, I'll show you the schematic diagram. So here we are considering the current variables, and we need to calculate the cost function. The system is not accepting the mathematical equations. So here we are optimizing the input selector. So we are predicting the next state value. So okay. So here you can see. So first we are considering the data, means while implementing the modulatory controller. So cost function we are considering the infinity. Then we need to have a certain data like idea, IQR, ID reference, torque reference. I have shown in the first diagram. So this set of data we need to have particular sampling interval. Then after having this data, now we are applying the. This is the only difference. I is equal to I is equal to 1 is to 8 for the 2 level inverter, because in the 2 level inverter we are having the 8 switching states. For 3 level inverter we are having the 25 switching states. I is equal to 1 is to 27. Okay, it will be make the that many intervals to get the accurate voltage vector. And for the 5 level inverter, I is equal to 1 is to 125. So this is the only portion changes for the 2 level, 3 level and 5 level. But the flow chart will be the remain same for all the topology, means all the type of the level. So now it initialize the voltage value, that is we need to identify the iteration to identify the accurate voltage vector. So we u of I. So what is I? I is equal to 1 is to 8 for the 2 level, and the for the 5 level 1 is to 25. We are optimizing the U. U means the voltage vector which we require. Okay, so now here we are optimizing the voltage vector. So for that, basically we need to have a minimum transition in a switch from the one sector to another sector. Okay, so whether we are having a minimum switching transition in a sector from one sector to another sector, if it is S, then it will go for the next step. No, it is not, then it will go for the again back. So it is going for the another iteration. So we are having a 1 is to 8, right? So I is equal to I plus 1. Then it will go back and then again do the, it will recheck whether the system switching transition in a switch is equal to 1. Then it will go for the down. Then at that time it will predict the DQ components and the torque. So this ID and IQ component will be predicted. So this is that one. So ID mathematical equation and this IQ mathematical equation. So it will predict the those values, and the torque equation also we were having. So it will predict when this minimum transition in this switch is there. So we will create based on the mathematical equation only. Now yes, after the prediction we need to calculate the cost function. So here in the prediction we are calculating the currents and the torque. So we will calculate the cost function based on the inputs of the current and then that one. So we are calculating the cost function. So the error between the actual value will be the predicted value and this is the reference value. So we are calculating the cost function based on this one. So now what is difference between the conventional method and then the current method? So this is the, imagine the cost function is nothing but the error torque. Okay, in the director control method, how we are finding the error torque? It is identified from the reference torque minus estimated torque. So this is the estimated torque is estimated in the previous state value. This is the output of the previous state. But in the model PT controller, how we are calculating the error? The reference minus of the current state values. Okay, so the error will be less we will get in the model printed case, but in case of the direct error control method case, the error will be more. So this will be the difference between the conventional one and then model printing one. So model printing one, we will always be one step ahead, whereas in the conventional one step behind will be there. So error will be less we will get in case of the model printing one. Okay, then if here the cost function means the error, whether error is small, yes, it will go further. No, the error is still more, then it will come back to the again for the another iteration, then it will go this process, and then it will identify, yes, now the error is minimal, then the error is minimal, then it will be optimize the u means the voltage vector value. Okay, so the u of t is equal to u of I at j is minimum. It means the cost function is minimum, the error is minimum. At that time, it is optimizing the u. Okay, so it will be optimize the voltage vector, and the same voltage vector is applied to the inverter. Okay, here we don't require any PWM modulator. So we are directly optimizing the voltage vector, the same voltage vector we are applying for the inverter. So this is the inverter switching how we are applying for the from the MPC. Okay, so this is the proposed modified diagram, and how I don't know why this is not. So now see, this is for the 3-level inverter. So the schematic diagram remains same, only the iterations changes. In case of 2-level inverter, 1 is to 8. In case of 3-level, 1 is to 27. So that many iterations will be made in case of the multiple inverters. So it may increase the computational burden, but we will get the accurate result. So the procedure will be the same for all the 3 cases. So this is the result using the 2-level inverter, 3-level inverter, and then 5-level inverter. So we will see the difference under different conditions. Okay, here I will show you the difference. So now the current THD using the 5-level inverter is 0.95. But the current THD using the 5-level inverter using the DTC space vector modulation is 1.68. So almost 60 to 70% is reduced by using the model PT controller, because it is predicting the next state value in the current state itself. So that is the beauty of the model predictive controllers. Okay, that's why the processing industries are utilizing this model MPC techniques, because it processes accurately. So that is the beauty of model predictive controllers and code flow chart. And we have compared with the latest literature, IET papers and IT transactions, etc. And our proposed method gives us the best compared to remaining methods. Okay, what is time? 12:53. Okay, so we'll see the hardware implementation also. So hardware implementation. implementation. See, when you are doing the research, especially on the drive applications, so hardware MATLAB, MATLAB simulation. So without hardware result, the publishing a essay journal is highly difficult for the drive area. In a polytronics or the drive case, without hardware result, publishing a journal, good journal is very difficult. Okay, so maintain the at least do the certain experimental results so that it is easy to accept the papers. So now, what is the difference between the simulation and then hardware implementation? So now the same diagram you have seen for the simulation. Okay, so this is the inverter part. Sorry, this is the inverter part, voltage source inverter, and this is the motor part. Okay, now the while implementing the hardware, what difference we will see from the simulation? So the only difference we will see, this is a voltage source inverter, power trans voltage source inverter available outside, and the motor also physically available outside. Then how we are communicating this physically available inverter and motor with the simulation? This is the diagram of the MATLAB simulation. Now this is the red line, this circle line, this is the inverter part and this is the motor. Okay, so this motor is sorry, inverter output is fed to the motor, and we are having the voltage source sorry, not voltage sensor and the current sensor. Those voltage sensor output and current sensor output we are feeding to the controllers. We will take the help of the controllers. You might be heard the D space, you might be heard the FPGA controllers, or you might be heard the microcontrollers. So we will take the support of those controllers and we will feed the measured quantities of the current and the voltages to that controller, and the controller output. The controller output, it means the switching pulses from the controller. We will write a logic in the MATLAB, and the logic which is we are getting from the MATLAB, it is fed to the again inverter. The pulses will be fed to the inverter. Those pulses are generated through the help of the controllers. IO ports you might be heard, input output ports. So by using the IO ports, we will connect the pulses to the inverter. And if you want to measure any output like speed, current, then the same controller has the DAC, digital to analog converters. So we have a scope. Okay, in the scope we have a probes. So the channels. So we will connect this DAC to the scope, and ADCs, analog to digital converters, the currents and voltage which we are measuring in terms of the analogs, and we will connect to the this one controllers. So the controller will change the analog to digital. Okay, so we need to have a one controller. Maybe it is a microcontroller, D space controller, or FPGA controller. Okay, so we have considered the two things. One is the this is the fellow or D space, and we can have some microcontrollers also. Okay, so with the see you can see the wires. So these wires are connected to the inverters. So all the feedback signals are given through the support of the controllers. So now the MATLAB is interfaced with the D space. So when we interface with the MATLAB and D space, then we can implement the experimental setup, and the pulses can be provided for the inverter through the D space. Okay, so inverter is available physically, motor also available physically. So see, this is the motor, this is the inverter. So the communication between the physical system and then MATLAB, there is a fellow, it is called it as a controller. So this is controller. So this is a encoder. So what is the quantity is measured? It is fed to the D space. And another controller also there. There is a microcontroller, TMS controller we call Texas Instrument Board. This is cost of 5,000. That is affordable range. So nowadays we are implementing with the support of this one only, because we have many PhD scholars. So we cannot able to provide the D space for everyone. The D space itself 5 lakhs or 6 lakhs cost, and whereas this TMS Texas Instrument Board cost of 5,000. Okay, we can afford a 5,000, not 6 lakhs. Okay, so even if it is damaged, then we don't bother that much. We don't bother that much. Okay, because it is a matter of 5,000 rupees. So the whatever the logic we are able to implement with the D space, the same logic we can implement with the this Texas instrument board. But only difference is if you want to see the four output or three output in the CRO, a scope. Here this Texas instrument board having the two ADCs, sorry DACs, digital to analog converters. Because of this, we can able to see only two results. We will see only two results at a time. So in the by using the D space, we can have eight result at a time. That type of scope you can have eight channel output scope. Then you can measure the eight quantities at a time. That is the only difference. This is that one. And these are the equipment we use for the hardware implementation and the parameter values. And these are the raw displays and their corresponding parts. And we have implemented all this logic in the MATLAB, which is interfaced with the displays. And you can see the result. So this is the display current. We are and current speed. So this is the display current. And the application model is coupled with the DC generator. And we are making the three currents. Now this is the operated at 150 RPM. So now this speed can be changed from the 150 RPM to minus 100. So now it is changing to minus 100. You can see here minus 100. Again we can change to 150. Now it is working at 150. And we can bring back to the speed. We under over 1 speed rate, our control is working. So here current people you can see we are getting more current people we are getting because we are using the two level inverter. So this is my three level inverter.
The mileage corresponds to the rotation of the
Hmm.
comes back.
Okay. So this is under three level inverter and this is under five level inverter. I'll show you the result. So we are operating with the five level inverter. Here you can see the current people. Here you can see the current people. Current people converge in case of the five level inverter. So this is current is there. For the different purpose, we are making only the three phase current and we operate at 1 Okay, so we have tested for the 2 level, 3 level and the 5 level inverter and we achieved the 5 level inverter is giving the best as compared to the 2 and 3 and under loading condition also we have tested and under different operating conditions like 200 to 300, 300 to 400 RPM also we have tested to satisfy the criteria of the EV applications. And again, reversal speed also we have tested. And this is the line voltages of the 2 level, 3 level, and the 5 level. And we have compared the results of 2, 3, and 5 with simulation and experimentation. So the experimental validation is always important when you do the research on the drive area. Not only drive, even powertrains also without hardware it is very difficult. And now whatever the things we implemented model PTU and the direct air controller, we are trying to implement on the EV vehicle. So this is the electric vehicle we designed in the NIT Andhra Pradesh. So the solar panel, 330 watt solar panel is connected to the vehicle, and it has a 6-phase PMS and drive of 2 HP, and we are working on it. So certain precautions we need to take while measuring the voltage. We need to take the what are the restrictions of the controllers. So we have used the DC-based controller. So the input voltage we can apply plus or minus 10 volt, and then current must be within the 100 milliampere. So you have to utilize the gain function. So if you use the gain, then we can reduce to the voltage within that. So this is up to this for this. And we'll see article discussion online. Uh,
Next level.
Thank you.
Dear participants, thank you for patient listening. So we'll break for the lunch and we'll meet again after the lunch.
We are modeling create some then when we go to the industrial level, we just go ahead
Yes. Today, as of today also industries are using the
but still the people is there, regulation is
they
there.
are managing with the uh, they don't want to invest more on the control quadrants. Okay, so they again they are experiencing this harmony capacity balancing problem, and industries always think that they want to invest less, want to get profit more. Okay, so again, this multiple inverter on paper it is there, but industry up to the industry level it is not there. Still they are applicable with the two level, and we are talking about the model PT controller and next session Vadlamudi controller, neural network, always there. But still PA controller there, PA controller there. PA controller is still there. So because they don't want whatever they are investing, they are compromising with small loss. Just PA controller is giving small loss. With that, their setup is sufficient. Okay. So why the industries are compromising with the 3-phase system? Why not they go for the 5-phase system? They will get the little more advantage. Uh, Suppose transmission system by limited to 3-phase. Power is equal to 3 times of the PA. So root 3 is the 1.73. 73% more power we are getting when we are uh, investing the 50% more. Means 2 phase to 3 phase, we are investing only 1 phase extra. Means 50% of the 2 phase. Okay. So but we are gaining up 73% output more. 1.73. 1.73. Okay. So they are going for 3 phase. Now if they go for the 5 phase, root 5 times. It means 2.23. So output increases, but why they are still in 3 phase? Because to go for the 5 phase, all the infrastructure they have to create. They have to create again 5 lines. That is అంటే ఇప్పుడు అన్ని లైన్స్ వేయాలి సెటప్ అంతా క్రియేట్ చేయాలి సో ఇట్ టేక్స్ ద హ్యూజ్ అమౌంట్ దాన్ ద గెటింగ్ అడ్వాంటేజ్ సో యూర్ 3 phase సిస్టమ్ 1.73 టైమ్స్ వస్తుంది మన 5 phase సిస్టమ్ కి వెళ్తే 2.23 అంటే లిటిల్ బిట్ మోర్ ఎక్స్ట్రా వస్తుంది కానీ నాట్ ద ఎక్స్పెక్టెడ్ సో వీఆర్ సాటిస్ఫైడ్ విత్ ద 3 phase that's why industries are not going further
వాళ్ళ కాస్ట్ చూసుకుంటారు సార్ పెట్టిన ఇన్వెస్ట్మెంట్
similarly, then we try to implement బాలయ్య
చెప్పండి. విన్నారా?
ఇప్పుడే
ఓకే. Hi, now we will start the Q&A session, and as of now, we have covered the simulation and experimental implementation of utility control method and data control method and volatility control. Uh, all these things, all these methods in simulation and experimental we have implemented. But the thing is that now we are going for the Now we are going for the sensorless control of EMS motor. So why we are going for the sensorless control of the EMS motor drive? Basically, here you can see the diagram. You can earlier case what we have done that we were measuring the speed of the motor. We are measuring the speed of the motor by using the encoder. Okay, so by using the encoder, we are measuring the speed of the generator. So when we are measuring the speed, so if some obstacle comes between the sensor and the shaft of the motor, then we are not able to generate the accurate speed of the motor. Okay, so in such cases, what happens? Uh, Wait a second.
So, dear participants, after the lunch break, we are starting the session. again.
Okay, good evening, one and all. Once again, welcome you all for the evening session. And so, as of now, we have discussed the feeder relay control method and director control method and director control method with space vector moderation. And also, we have discussed model creating controller methods for getting the accurate torque and flux performance by enhancing the drive performance. So up to now, we have done this simulation, and we have also seen the experimental validation, and have shown the setup and all the experimentation too. So all these things, all these methods have been implemented by using a speed sensor, that is the encoder. Okay, so we have one encoder was attached with the DC generator to capture the position of the speed, speed, rotor position. Okay, so now the thing is that if some obstacle so comes between the encoder and then shaft, then what will be the situation? So here we have seen such cases also. So if some obstacle comes between the sensor and the shaft, then the error between the imagine the reference speed minus the actual speed gives us the error. So in that case, the error will be lost, and we will get the deferred output result than the required output. So how can we avoid from such kind of situations? So in order to come out of such kind of situation, there is a one way, that is the instead of speed measuring, instead of the position measuring, we can estimate the speed by using the measured quantities of voltage and the current. Basically, the voltage and currents are measured by using the voltage and the current sensors. So, by using this voltage and current measured quantities, we can estimate the speed so that we can eliminate the speed sensor without sensing the speed. So, this is the advantage of the going for the speed sensorless control technique than instead of the going for the sensored method. Okay. So here in the literature, there are different types of speed estimation methods are available in the literature. So there are observer kind methods, and then the another one is the model based methods. Observer kind, there are different types again. The extended Kalman filter, and then sliding mode observer, and then extended Lowenberger observer kind. So it's different methods are available. So each method has its own advantage, its own disadvantage. So these methods are depends upon the application oriented. So now the first method is the extended Kalman filter. It gives a good performance. The thing is that it requires the huge mathematical equations. So system is more complex. So in a similar way, the lower particular observer also required a high mathematical complexity. So because of this reason, when we are going for the high level of the mathematical equations, so we need to have a very high computational capacity systems to execute these programs. So, we need to have a high computational DSPs to digitally execute these methods. So, there are certain limitations. These are those limitations by these methods. And then another method we have the sliding mode observer. Though this method has less mathematical complexity, but this method need to have a one gain function we need to have in the mathematical equation. So if you don't tune the gain value, suppose beta gain value, then it will create the chattering phenomena, thereby it increases the ripple content. So these are the about observer kind of methods. Then there is a another method available in the literature is that model reference adaptive system. So a speed estimation technique, speed estimation method, the block is created by using the mathematical modeling of the motor. Okay, so the types is available: stator current type, vacuum type, and then reactive power. So as I said earlier, so every method has its own advantage and disadvantage. So each method is a certain application oriented. So based on our application, we need to consider the particular one. So for our case, we have followed the stator current one because we are dealing with the current quantities. So back EMF base it creates the problem at low speed operating condition. So we are estimating the speed and we are providing these cases for the electric vehicle application. So electric vehicle may run at low speed, high torque cases also. So that time also this method need to tune properly, the estimate the properly. But the back EMF based model difference adaptive system unable to estimate the speed accurately under low speed operating condition. And this reactive power method also has a instability problem over a wide speed range. So by considering all these methods, we have operated with the stator current model, stator current model adaptive system. So now this is the schematic diagram. So this schematic diagram is the DTC with space vector modulation. Now what is the change from that diagram? Earlier we have connected the one encoder with the shop. Now this connection were removed and now we are estimating this actual speed with the support of estimating methods. So this is that block. So what are the input variables for this estimation block? The input variables are the measured quantities of the voltage, the measured quantities of the currents. So by using this measured voltage and current quantities, we are estimating the actual speed. So now this is the model reference adaptive system method. Here we have three blocks. This three blocks is the reference model, and this reference model being created by using the mathematical equation of the motor. Okay, so IDS and IQS, and similarly adaptive model we can also call it as a current model, and this is created by using the measured quantities. So this is also purely mathematical equation. We have designed, created the reference model and the adaptive model. So where adaptation mechanism is based on the this is the reference model mathematical equation. So this is the mathematical equation we have taken for the model. Okay, so ID and IQ. So here the inputs of the this reference model is the ID and IQ, and this is the mathematical equation of the ID and IQ. And then adaptive model, this is the adaptive model, and the inputs and output is the estimated ID, estimated IQ. So this is the estimated ID and this is the estimated IQ. Okay, so we have created by using this mathematical equation, and we are estimating the rotor speed instead of the measuring the rotor speed. This is the equation. And here also we need to have a 1 kp Ke values are required in the adaptation mechanism to minimize the error. So these values also we have taken kp and Ke values. So here for all these three cases we have estimated the speed. Now carefully if you see this result, so there are two different lines are three lines are available. This is the reference one, and this one another line, and the blue one is the another one. Orange one is the different one. So the orange one is the estimated one. This blue one will be the actual one, and this is the estimated one. So the point is the estimated speed is accurately tracking the actual speed, but the thing is that while using the two level inverter, we were having little bit uh, ripple current were observed in the two level, but that ripple current is not available in case of the 5 level inverter, but the line is dragging smoothly with the actual speed. So the point is that though there is a ripple content, but the estimate speed is estimated accurately and it is tracking the actual speed. So to compare with the actual speed performance, we also tested. I mean, we have shown the actual one and then estimated one. It means the system which we designed is accurately tracking the speed, and this is under loading condition. Okay, so this is the case we have designed the means we were estimating the speed of the motor. Okay, now the point is that so in these equations, so we have the parameters of RS. Okay, so this is the parameters of RS, ID, LD, and LT. So the major function means if you operate a machine entire day, 365 days. Okay, so without non-stop, if you operate a machine, so the temperature keeps on increases. So when the temperature increases, then what happens? The stator winding resistance keeps on increases. Then thereby what happens? The voltage drop keeps on increases. So if the voltage drop increases, then losses will be increases. Then how can we avoid during such conditions? So this method is the parameter centric. It means RS is the parameter. If throughout day is operated, then RS may increase. So we have to estimate the RS according to the means duration we are operating. Okay, so that we can get the accurate performance and we can control the variation of this. Means we can change the RS according to the requirement. So we need to tune the means we need to estimate the RS also parallel to the speed estimation. So here what we are doing, we are estimating the speed and parallelly we are also estimating the stator resistance so that we can balance the performance. Okay, so now we are estimating the stator resistance in parallel to the speed estimation. Okay, so now this is the portion of the speed estimation and this is the portion of the stator resistance estimation because the reference model is the stator resistance is the part of the reference model. So we need to tune the RS values for the getting accurate performance. So we are parallelly estimating the RS at the same time omega R. So this is that block diagram for estimating the stator resistance. So here also we have the reference model, we have the adaptive model, and we have the adaptation mechanism. So here this reference model and adaptive model we have designed. So based on the mathematical modeling of the PMSM motor. So here these are the equations we have taken for designing the stator resistance estimation. Okay, so this is the adaptive P adaptive we have taken. So for the adaptation mechanism, adaptive model design purpose, this is the that mathematical equation. And here we are estimating the RS estimation. Here also we are taking the one PI controller to minimize the error between the P reference and the P adaptive. Okay, so wherever the difference means the reference minus adaptive estimated, so we need to have a one controller. So that controller we are taking it as a PI controller so that we can minimize that error. Thereby we can enhance the performance. Okay, so by using entirely the mathematical equation only, we are designing the stator resistance estimation, and we found this result. Okay, so here this result we have shown the currents and the speed and the torque, and here stator flux, and the last fellow is the stator resistance. Okay, so now here what we have done that if we change the stator resistance, see, when we have started the maximum value of the stator resistance is 0.09. So the value of the stator resistance is 0.09. This is a PMSM motor, that's why the value is 0. We will have a very less resistance in the PMSM motor. Okay, so now we consider that we have varied the stator resistance little bit. In this case only. Okay, so here we have varied the stator resistance from a little bit. In these conditions also, we are not get the means we are getting the accurate result only. So means we are properly estimating the stator resistance and thereby we are getting the proper output. And this is under loading condition, and this is the under different speed conditions. Okay, so here intentionally we have changed the stator resistance from zero point 0.09 to zero point 0.08, some very small value we have changed, so thereby we are getting the standard performance we are getting, so actual speed tracking the estimated speed. Okay, so this is about the stator resistance estimation and then speed estimation method. Okay, so now the another method we have implemented is the fuzzy logic controller. So why we need a fuzzy logic controller? So basically the actual speed we are measured by using the encoder or estimation methods. So the actual speed is compared with the reference speed and the error speed is fed to a controller. So what is that controller? It may be a PI controller, it may be a optimization method, it may be any artificial intelligence method. Okay, so up to now we have used it as a PI controller. But what is the drawback of the PI controller? The drawback of the PI controller is that we can set the KPK value for a particular speed position or for a particular load position. If we change the speed value or if we change the load value corresponding to these values, we need to change the KPK values also. But we need to stop the operation and then we need to change this one. Okay, so then only we may get the accurate performance. But this is not possible in a online means in a while running condition. The changing of KPK is not possible. There are certain methods of tuning of KPK value in online also observed method type, but it is little bit more complex. That's why we have not gone to that level. So what we have done that instead of using the PI controller, the PI controller is replaced with the fuzzy logic controller. So the fuzzy logic controller we have replaced with the PI controller. So remaining part is same. Remaining everything is same. Only the PI controllers are replaced with the fuzzy logic controller. So now here we have, this is the error we have taken the two inputs and one output. So the two inputs are, we have taken the error speed as a one input and another input we have taken as with little delay. So by applying little delay function we have taken the change in error. For accurate error speed, error means for the accurate output of the electronic task, we have taken the another input also. So this is the error means T is equal to Kp of error speed plus K of integral of error speed, and this is for the change in error speed. So that is this is one I was saying. So this is the actual reference speed and this is the actual speed. The error speed is fed to the earlier one PI controller. Now the PI controller is being replaced with the fuzzy logic controller. So this is the error speed we can consider as a twist in values. So in terms of the number, so integer values, so twist values we can consider. So here error speed and then with a little bit delay. we have taken another input, but the getting a proper result. Two inputs we have taken, two input, one output. So in the fuzzy logic controller, there are different set of blocks. So the first block is the fuzzifier. So what is the purpose of this fuzzifier? So this fuzzifier linguistic activates the linguistic rules. It means here we are providing the crisp value. So the crisp value being converted into the fuzzy sets. The crisp value being converted into the fuzzy sets. So it will be done by the fuzzifier. The crisp value will be converted into the fuzzy sets. And here we have a certain rules in the inference. So basically this rule will be created whether you are going for the 3 by 3, 3 by 5 or 7 by 7, 9 by 9 depends upon the inputs, whether it is a single input or double input or multiple inputs. So this method can be applied for the multi inputs and multi output or multi input and single output also. It's up to the applications. And here rule base can be extracted based on the knowledge which we gain from the previous operation. Like this is the case, we will get the output. This is the output we will get when KPK values are this much. So it means based on the past experience, we can create a rule base. Okay, so that rule base can be a 5 by 5, 7 by 7. It's up to the error minimization level. And then the defuzzifier. So here we have seen the fuzzifier. What is the purpose of the fuzzifier? It is converting the crisp value into the fuzzy sets. Defuzzifier means again invert. So fuzzifier sets to the crisp value. So the defuzzifier provides the output value in terms of the crisp value instead of the fuzzy sets. So this is the process of the fuzzy logic controller. And so we have two inputs. One is the error speed, another one is the change in error speed, and I have taken only one output variable. So that is the torque, electromagnetic torque reference. And here we have considered 7 by 7. Then why 7 by 7? So we thought that we have gone for the little bit minor to the up to extreme level, means based on the error gap, error bandwidth up to this level we have considered, so that in the all the conditions we may get the accurate performance. That's why we consider 7 by 7. Maybe 9 by 9 also we can consider, but for the 9 by 9 again we need to write a rule base 9 into 9. So that many rule bases we need to create. So it may create a little bit complexity here. 7 by 7 49 we have created. So again 9 by 9 means we need to create 80 plus. So it is creating difficult, means there is a system complexity increases. The burden on the compressor increases. That's why we limited up to 7 by 7. And this is because with the type of fuzzy logic controller. So if you search in the literature, so you will find the type 2 fuzzy logic controller or interval type fuzzy logic controller also you will identify. Then why people are going for the type 2 fuzzy logic controller? So this is that block diagram of the type 2 fuzzy logic controller. So if you see this diagram and the previous one, everything is same except the defuzzifier block. So in the defuzzifier block, we have a type reducer. So if this is the type reducer, we will get the advantage. So we will have a many arbitrary transaction on type 2 fuzzy logic controller also. So I'll explain this method. What is the difference? So here, this is the type of fuzzy logic controller membership function, and this is the type 2 fuzzy logic controller membership function. Now, at a particular instant x, that x dash. So if we draw a line straight on the membership function, at this instant we will have a one particular crisp value. Okay, so here we will have a maybe zero point 0.4 or zero point 0.5 something. We will have a one particular crisp value we will get from the type of fuzzy logic controller. So similarly, at particular instant, if I draw a straight line and it will be cut on the type 2 fuzzy membership function. And here, if I project the same thing here, then we will find again a fuzzy membership, fuzzy membership function between the zero point 0.4 to zero point 0.6. So this is the method. This is the method we can call fuzzy within the fuzzy. Okay, so here we will have a multiple membership function embedded within the fuzzy, thereby it will handle the minor uncertainties and provide the better performance compared to this result, because it provides a crisp value but here fuzzy within the fuzzy. Okay, so this is the beauty of the type 2 fuzzy logic controller, and this is the difference between type 1 and type 2 fuzzy logic controller. So fuzzy within the fuzzy, again we will get the membership function between zero point 0.4 to zero point 0.6. So this is the type 2 fuzzy logic controller advantage. It will be more accurately provide the output result. But the in the MATLAB we will not find easily this type 2 fuzzy logic controller, because the we need to dump the means the program, and this is not released by the up to 2024. Maybe MATLAB may release in the 2025, because they have to procure from the who has developed the type 2 fuzzy logic controller. So we have taken the permission from the inventor, and he has given with the certain condition that we should not we should not give to anyone else. Okay, we have procured one book of this author, and they have given the access. Okay, and this is also we have implemented the same by 7 by 7 level 7 by 7 membership function, because we need to compare with the type of fuzzy logic controller. So the same way we have implemented, and this is under no load condition. This is with the type of fuzzy logic controller, and this is type of fuzzy logic controller, and there is a slight difference between the type 1 and type 2 fuzzy logic controller in the output, and we can identify here. So here we have huge notches and the drop, and here we have less drops in the notches. Okay, this is up to fuzzy logic controller. Then, in addition to the research works, there are participants from the PhDs, and there are participants of interested in doing the future higher studies. So for them, I thought to give certain suggestions. That is how to write a research proposals or the project proposals. Those who are working as a faculty, for them they can draft the proposals for the DST or any other collaborative proposals, and who are interested in doing higher studies, so they can prepare the research proposals, because we are seeing nowadays the many people are coming for the PhD. PhD interview purpose, but they are not being qualified because they are not coming with the proper objectives. Okay, so you have to prepare and come. Nowadays, earlier days are different, but nowadays you have to come with proper objectives. Okay, so during the interview, we were asking, so in which topic you are interested to work. Many people are saying that I am interested to work in the power electronics. Power electronics is a ocean. Okay, so what objective you are interested? So then he started saying that I want to work on the buck converter. Buck converter. So BTech level they have done buck converter. Then what you will do with the buck converter? Okay, so we need to go with the particular objective. Then they will start, okay. This is your objective. Then have you implemented at least a basic level? They'll start asking next question. Then your answer will be no. Okay, so before approaching any committee, so do start doing the some basic work. Okay, so the PhD we need to complete within the stipulated time, but we need to do work the advanced methods. So if you don't do those basics at the before attending the interview, then how can you implement the advanced control methods? Okay, so they will test all these things. So if you can go with the proper objectives, then there may be a huge chances of the selections. Similar way, while drafting the research proposals also. So many people are writing a research proposal without any background, means supporting documents. Okay, so suppose the one person, there are two persons. One person is writing a project proposal with proper backup in the sense he already started the working on that area, and he has published one or two journal paper in that area, and he has attached the certain proofs of the simulation result. Suppose a person is intention is to implement the 5 level inverter fed PMSM drive for the electric vehicle application. The fellow has already implemented the 3 level inverter, 2 level inverter for the PMSM drive, and he has left only with the implementation of the 5 level. And that fellow already has the experience of the implementing the hardware setup on the induction motor drive, and that fellow already has the publication in the last 5 years on the induction motor. He may not have the publication on the PMSM, but he has already publication on the induction motor, the AC drive. Okay, so this is that person. The another person might have the good objectives, but he don't have any supporting documents. He might have written the good project. Okay, so see, not you might have many imaginations. What is the supporting documents? So imagination cannot be solved within the 3 years, right? It may require 5 years or 7 years, but these project proposals are the time stipulated, right? So how can I believe your idea will be worked? Okay, you may able to implement that one. How can I believe? So in order to believe, you have to provide certain proofs that I have already worked in this area. These are my publications, and this is my simulation result. If you give me the opportunity, then within this time, all the projects are time specified, right? So within these 3 years, definitely I will implement the hardware and I will provide the result, because I have left with only hardware, or I have left with only small minor work of the simulation and the hardware implementation. Then there is a chance of high sanction rate. Okay, so you first give me the project, then I will start working. This is not the generation today. Okay, so implement and go for the extension little bit and ask for the projects. Then industry is ready to sponsor such kind of projects. Okay, then that is the way we need to be ready. That's it. So uh, first impression is the best impression, we always say. Okay, whenever we are saying one object or one something statue or something, so we what is the background we will not see. We will see the look. Okay, so if I wear a proper dress, then okay, attire will be good. So similarly, the title of the proposal. So the title must reflect what you wanted to implement. Okay, so the title must be attractive. Suppose this is the paper I have written. In this paper, my intention is to implement the 5 level inverter for a PMSM drive with the control scheme. Okay, so that method I have written means the director control method with space vector modulation, and the I will also implement the 5 level. It means I will compare with the lower level, 2 level and 3 level also, and which is applied for the EMS motor. It could have little bit more, but like which applications, the electric vehicle applications are, this method is implemented to reduce the torque for reducing the torque people little bit, but the paper has certain word limit. Because of that word limit, we is not able to extend little bit more. Okay, so the thing is, the title of the project proposal must be attractive, and it must suit for the current and upcoming generation. Okay, the current trend is the electric vehicle applications, drone applications, and then the renewable applications for the electrical students, electrical people. So your last word must reflect certain applications. For what application your project proposal suit. Okay, and then in the project title itself, whether are you going to implement a hardware or only a simulation. So if you say I'll implement only simulation for the drives, power electronics, then even in the power system or microgrid or smart grid also, it's very difficult to get the project proposals. At least you have to implement with the real time. So the design and development of or implementation of. So some little attractive words must be there in the title. Okay, so the people will see when we open the book or something, so we will go by seeing one by page by page by seeing the starting only. Okay, one impression we will get. So likewise, we need to create that environment while writing the project proposal. Okay, and then these are the certain sanctioned project. The first one is someone else, and the second one is mine. So the design and development. Second one also design and development. Design of a portable emergency ventilator during the COVID period. This project was sanctioned. And then the fifth one is the design and development of multi-input, multi-output power converters. And then modeling of Wi-Fi propagation like that. Okay, so see all the titles are beautiful. So what they wanted to implement is reflecting in the title itself. Okay, so they create title such that it attract the more, and then the objectives. So there are certain word limit for the writing the project objectives. So we need to write in a crisp manner our objectives. Okay, so we need to write properly all the objectives, and then many people, as I said before the starting of these slides, many people are saying that give me a project, then only I'll start doing work. Okay, this is not the scenario today. Okay, so attach the some result of previous one, then okay, I have done my project is the implementation of the 5-level inverter, and I have already implemented with this is the 5-phase PMSM motor. This is the 5-phase PMSM motor and sensorless PMSM drive of the 5-phase PMSM motor with 3-level inverter. So what I have attached the proofs, I have attached the proofs of the two conference papers, and I have attached the simulation results of the 2-level inverter and the 3-level inverter, and this is the 5-phase PMSM motor and the torque and the speed result, and I have informed that I have already implemented the 2-level and the 3-level and only left with the sensorless speed control. Okay, I need to implement the sensorless one and I need to implement the hardware one. Okay, then though I have implemented the simulation one, only sensorless technique is left for the simulation, and the hardware I have left entirely because I don't have the 5-phase motor with me. If he sanctioned me the project, I will purchase from the sanction budget this drive, then I will implement the 5-phase PMSM motor result. But for that support, I have given the previous project supporting data. Like I have already implemented a project on the 3-phase PMSM drive with 2-level, 3-level and 5-level and sensorless technique. Okay, so I have already have a experience on the developing the project on the PMSM motor with 3-phase and implemented the simulation on the 5-phase and produced the result. If the project being sanctioned, then definitely I will implement the hardware within the 3 years. Okay, so this is that way I have projected the my I have drafted the research proposal. Then the reviewer may get the confidence. Okay, he has already done the one project. He has already have a implementation of the hardware exposure, and The present project he has already 40% implemented, only left with the 60%. Okay, so that way we need to bring him in towards us. Okay, when we attend for an interview, if we go by preparing certain topics or some project, if one of the person like our project, he will drag us in that way only, in that project only. Then we are the expert in that area. Then we can confidently answer for those questions. Okay, we need to bring them in our area. Okay, so in that way we need to prepare the research proposal. Okay, sometimes luck need to be also favor. ఓకే సో ఇన్ తెలుగు ఆవగింజంత లక్ అయినా ఉండాలంటారు కదా ఓకే సో ఇఫ్ యూ వర్క్ హార్డ్ ఫర్ 99% బట్ అట్లీస్ట్ యూ నీడ్ టు హ్యావ్ ఎ లిటిల్ బిట్ లక్
For the first time project proposal writing, we don't have any hardware experience.
బట్ యూ మే హ్యావ్ హార్డ్వేర్ ఎక్స్పీరియన్స్ ఇన్ యువర్ పిహెచ్డి యూ మే హ్యావ్ హార్డ్వేర్ ఎక్స్పీరియన్స్ ఇన్ యువర్ డిపార్ట్మెంట్ ఓకే సో దోస్ థింగ్స్ యూ కెన్ అటాచ్ రైట్
Okay.
See, I am not asking you to produce the same hardware. I am asking you to whether you have any exposure. Otherwise, I'll think that the implementation of hardware, the person who has implemented the hardware to implement other kind of hardware itself difficulty. Without any knowledge, how can he implement the new project? So such kind of doubts we will get. Okay. So then we need to flow with Gantt chart, means the timeline for the 3 years, what way we will go. Means for the first 6 months, what we will do like that. So this is also we need to prepare a little bit carefully, but this is not that much important. But we need to create it properly, and this is one of the important thing. Budget plan. Never ask more. Asking more, asking too less, both are rejected. Okay, this pointer may cost of 2000 rupees. If I ask 4000 rupees, I know what is the cost of, because the project reviews goes to the particular faculty who is the expert in that area. Okay, so I know the cost of this pointer, maybe 10% less, plus or minus. So if you ask for plus or minus 10%, it may be okay, because maybe sorry, cost may increase. Okay, so 10% okay. So if you ask instead of 2000, if you ask 4000, then straight away he will write a comment, because after evaluating the research proposal, we need to fill the data. For each point, there are 200 to 500 words we need to write. So 200 means one paragraph we need to write. So what we will write the paragraph? Because this fellow has given a proper justification for this pointer. This pointer comes in the approximately that cost only. So the budget plan he has made as per the market rate. So before writing a proposing the budget, we need to have a market survey. What is the cost of this pointer? If possible, we need to attach the means nowadays they are not asking. Later the quotation they ask, then we need to be able to provide. Okay, so we need to provide this budget plan properly with justification. So this travel and contingency travel is fixed. That is up to the project maximum they are giving 50,000, 50,000, 50,000 for the DST project. So if it is 3 years, then 1.5 they are fixing, but they are not keeping the limit for the consumables. You can ask any budget for the consumables, but need to be a proper justification. Why you need that many consumables? Okay, so that one, and the research equipment also we need to propose properly. Okay, so you are doing the work in the some area, but you are asking other equipment. So how it is relevant to that work area? Okay, so that is also one. So and for your work you may need one JRF. If you ask two JRF, Okay, they will not be. Okay, so if you propose 1 crore rupee, they may give 60 lakh. That time if you reject, we don't have any option, but we have to take that one. So by taking that, we may compromise of taking the research fellow, or we may reduce the certain equipment, and we may ask the institute, sir, I have granted the 60 lakhs. In that 30 lakhs being given for the equipment, can you provide me the equipment which is available in the institute, in the department, so that I'll execute this project. After the execution of the project, I'll return that equipment in the department. Okay, so there is no guarantee that whatever the budget you are proposing, though it is accurate, though it is the market value rate, sometimes they may cut down the budget. But if we request, sometimes they take the request, but sometimes they don't entertain it. Okay, so this happens. So budget also we need to plan properly with market rate, and then this is one of the important thing. Again, the research team. So nobody can be Ekalavya, maybe some. Okay, why? Because maybe any person may struck up at particular point. Okay, at that point somebody can help. Okay, whether that somebody is available with you or in your collaboration, he may not physically available with you, but will he available over online or something? Means whether he is available somewhere. So then who is he? That says the research team. So if you stuck somewhere else, the somebody need to be there to bring throw out you from that strike. So you have to provide his details and what is his expert. Okay. So nowadays there are some people, they are giving the some X person data, and the project proposal review is going to the Y person, but this Y person knows the X person. You have written the project, you have given data information like the X person will help me if I stuck somewhere, and the project, this proposal went to the review for the Y person. The Y person knows the X person, both are friends. There is a chance he will ask, have you given consent to implement this project? This happens, and this X says, I don't know that person. Then they may seriously complain the that DST or somewhere else. Okay, so inform anyone if you are keeping their names. Okay, so not only there, if you are writing a paper, take any data, but you have to cite. Okay, so if you are using someone data and if you are not citing, they will be more serious. Maybe there are very less generous people may be there, but it is offensible. Okay, so take their data, cite them. This is the data I have taken from them. Then they will get the credit and you will get the profit. You will get the advantage. So they may not go to the beyond the level. They may, okay. At least he has mentioned this is mine. This is not his. That is belongs to me. Okay. Yeah. Right. Okay. So images and certain equations will not come from in the logarithm, right? But images that they are, people are taking, they are not citing. Suppose that experimental setup, that fellow might be implemented somewhere, but you don't have proper experimental setup. Huh? So the schematic diagram which I have drawn, he might not drawn, but he has implemented it. I have drawn that beautifully, but he unable to draw that one because of he don't have that kind of software. But he has taken my picture. Then those things. So research team must be given properly. He may not be required to be present in every institution. He may be anywhere else, but his consent and his name may be helpful. And then the last 5 years key publications they majorly see. So we need to provide these details. So I have given this data while getting the project. So these are all belongs to the same area papers. and then these are the certain costs. These are the previous data. Now all this name changed to the ANR. Okay, so this is the best same. The scheme is same. The name only changed to the ANR. Okay, so the core guarantee, everything is there. The name only changed, and there are certain other DST counts also there. And okay, so while evaluating the project proposals, what are the points we need to write? Means the first one is the merit and impact of the proposed research. We have to write 200 characters, minimum 200 characters we need to write. So we need to thoroughly read the merits and how it impact the current generation. We have to write that one also. And then the comments on the innovation and the impact of the proposed activity. We have to write 200 minimum characters we need to write. And then expertise of the researcher and the collaborators. So in what area I am working and who are the collaborators along with me. So we have to write the minimum. Okay, this fellow has a expertise in this area, and this fellow has the collaborative, and they are expert in that area. So we will write those points. Okay. So all this data we have to fill a minimum of 150 to 200 characters. It means we need to write, we need to read the thoroughly because this is a research proposal, right? And then resources and budget. This budget, whether these budgets are like consumable equipment, whether these are appropriate, too less, too more. Appropriate means it's okay. And detailed comments on the above. Means all these three we need to write 500, minimum of 500 characters. Okay, so each budget we need to mention. And then general comment about the project proposal as a whole, and then any comment for the benefit of the PA, and then at the last recommendation. So whether the research proposal everything is okay, then we will make it 10, and the overall rating out of 10 we may give 8, 9. So these are the things I have reviewed a few proposals. So from there I have taken this data so that somebody may get helpful because these people are seeing these kind of things. So means we need to prepare budget and everything in a proper manner. And the reasons why the research proposal can fail because of lack of proper objectives and misleading data set, etc., etc. So and no proper justification for the budget proposals and asking too much and asking too short. And there are certain focus area this is already done model predictive, but instead of the model predictive, the model predictive also required a model itself a mathematical model. Now we are concentrating that without a model, without uh, means we are maintaining the parameters of the PMS model, we want to create a model free. So now we are working on the model free and then also working on the machine learning. Nowadays, the machine learning also not limited to the certain department like computer science. Now it is adapted by the many. So now we are working on the machine learning. So now the PI controller we want to replace with the machine learning, and then inner loop also we want to run with the machine learning, so that based on the parameter change or any reference change, it will act automatically. So we are working on now machine learning based PMSM drive, which are really essential because the future will be the autonomous vehicles. Okay, so future definitely will be the autonomous vehicles, and so for which we need to have model predictives and machine learning, and then the future is not limited to 3 phases. So the future people will go for the already they have started on the 5 phase. I am not talking about the generation side. So I am talking only the drive area. Okay, so if you are talking for the generation, then of course by going for the multi phases or polyphases, more than three phases, then the generation side we will not get that advantage. But I am talking about the drive, because if I go for the multi phases, there are certain advantage I get. I give you the light idea. If one of the phase being faulted is open circuit fault or short circuit fault. If one of the phase is faulted, so we will have at least four phases. Then the faulted phase can be made thrown on the remaining four phases, so that we can get the, means we can maintain the output. Means if we want the some 5 kilowatt motor we want to operate, the same power we can balance remaining the 20% on throw on the this remaining four phases. Okay, that is the compensation of the faulting of this one. Or another way is that another advantage we will get when this phase is faulted. At least the PMSA motor we can operate in the with the four phases. If three phases, we unable to get the proper output with the two phases. At least we can operate with the four phases. Thereby, we can get the approximate behavior of the PMSM motor. So this is one. And nowadays, we are going for the electric vehicle for the transportation purpose also. So the transportation vehicles are required a huge power. So while going for the huge power, we need to have a multi-phase. Okay. Then when we are going for the multi-phases, then we can reduce the torque report. Okay. Multi-phases gives us the smoother performance. Okay. So that is one advantage. And per phase currents. So per phase current also reduces. So these are the certain advantage while going for the multi phases for the drive application. I am not talking about the generation application. Okay. So for going the generation, three phases is sufficient, because the advantage we will not get much for going multi phases. So this is the one area we are working now on five phase EMSN drive, and this is the another area now we are working. So here we don't want to use any model. So we want to implement with the model free. Okay, we don't want to use any PI controller. We don't want to use any model free controller. We want to have a model free, so that we can apply to any kind of AC motors, and we want to operate for any kind of the inverter. There is no restriction, 2 level, 3 level, 5 level. So the generalized inverter we want to utilize. So now we are working on it, and of course we want to also implement a fault tolerant also. If one of the phases are faulted, then we need to balance that faulted phase on the other phases. And these are the certain four wheelers which are using the five phase and the six phase motors. So this is the Skoda buses using five phase, and this is the Audi using six phase, and this is our six phase. Likewise, there are vehicles already being implementing with the five and six phase. Okay, these are
in Tesla,
three phase.
three phases.
Okay, so these are the things, and so we'll stop here. So we have also implemented the solar tree basically. Uh, why we are going for the solar tree means to reduce the space. Like in the parking places, we can create a tree and we can park the vehicle under the tree, and we can implement a 5 kilowatt solar tree within a space of 4 by 4. Okay, so the space is required very less, and this kind of things also we can implement with the UG and PG students. And this is the one on the we have implemented in our means in our institute. So this is that 960 watt, and for the water pumping application we were working, and this is that the 960 watt solar power tree. So the space consumed by only 2 by 2. Okay, this is the pole we have fixed in the ground, and the remaining thing will be on the tree. So the ground, everything we can utilize for the maybe parking purpose or may utilize for the any cropping purpose. Okay, so this is that, and so, article discussion, we can see, as I said, how to draft a research proposal. So, in the similar line, we need to write the papers also. Okay, so especially while writing the papers, the drive application or powertronics applications, so we need to have a hardware exposure. So, with the hardware exposure only, we can able to write, we can able to publish the papers in the SCA SCA. So, so this is the paper of the 5 level inverter fed DTC with space vector modulation of permanent magnet signals motor drive. This concept we have already seen in the morning session, and so here we have written the contents of introduction, and in the introduction we need to write everything. Everything means who has started. So here we have PMSA motor, and we have proposed the DTC with space vector modulation. You are the one who introduced this concept, or anyone else introduced already. Then, if they have already introduced, then what you are going to enhance from the existing one. So we need to write a abstract clearly, and then in the introduction we need to write who has started in case of the PMSM motor, and then whether you are only one who proposed this 5 level inverter or somebody else already proposed. So all the data we need to highlight, and we need to cite them properly, and we have to draw the schematic diagram with neat sketch, and so here we have cited the previous expert who has written the different methods and field rate control method, direct current control method, and somebody has written the paper with DTC specific modulation, but they have proposed with only 2 level inverter. Then we have written the 5 level inverter. So then we need to show the difference, and dynamic modeling of the PMSM drive also we have given, and their mathematical expressions we have given. So, and whatever the things we have discussed in the morning session, how we are converting the 5 level space vector modulation into the 2 level. So the same thing we have mentioned here. So we have already seen in the morning section, and we have provided with the simulation result. So simulation result under no load torque, we have seen this result also under no load condition, and this is under loaded condition. And we have also seen this speed result under different speed changing condition from 1500 RPM to minus 1500 RPM, and again minus 1500 RPM to 1500 RPM. And then we have also explained the how we have implemented the hardware and implementer, which we have discussed afternoon. And so this is the hardware setup which we have seen already, and how we implemented also we have seen. And these are those results we captured, and supporting data we have provided for the publication. And we compared the hardware result with the simulation result, because uh, here we are comparing the hardware result and the parameters also we need to give the same. Okay, so after maybe while doing the simulation, you might not have procured the motor, but after procuring the motor, then you have to take the parameters of your motor, and then the same parameter you need to dump into the simulation, and then take the simulation result and compare with the experimental. Then people will consider. Otherwise, they may ask in the comment section that whether the parameters of the simulation, the experimentation is both are same or different. And then we compared, and then what we get the benefit from this proposal, we have written clearly, and then we have acknowledged this in the here this work we have done with the support of the DSP sponsoring project. Then I have mentioned their acknowledgement and their project sanction number, and then the references, valid references in supporting of the this application. And bibliography I have given. So this is the one paper, and there are multiple papers I have, but to the time constraint, I will show the certain papers, and this is the one we have discussed, and then this is the other one we also discussed, that is performance analysis of multi-level quantified sensorless BMSM drive. So we have also seen the sensorless methods using the modified model PT torque control. So we also discussed the model PT controllers. So this is published in the year of 2021, and this is the fellow Dharmendra Kumar is one of my PhD scholar, and now he is working in R&D, one of the R&D Epogen. It's ED based R&D, and then the Pudrao Ramakrishna, Putra Ramakrishna is another scholar, and now he is with NIT Jalandhar as assistant professor. He has selected there. So they are my first two scholars now in good position. So these are the things we already discussed afternoon section, and the mathematical modeling on the PMS model, and how we propose the this model predictive controller, and what is the advantage with that, and this is the schematic diagram of model predictive controller. I have shown in the previous slides also, and so and so we have also seen this flow chart. So the process of the model predictive controller step by step. So how we are estimating means how we are calculating the cost function, and further process how it is going on. And,
You are using this sensorless methods
hmm.
using the estimation or prediction. So, the cost-wise, any advantage is there?
Yes, cost-wise advantage will be there because we don't need to purchase the speed sensor. So maybe it is a 2000 or 3000. That much amount we are
But
saving.
complex still in the mathematical complex.
Yeah, see, that will be on anyway. Our systems are that much, at least that much capable. So little bit increases. Mathematical complexity will be increases.
Any other advantage apart from cost?
First advantage, not the cost is not only the advantage. Cost is the secondary. The first advantage is that, see, our motor is running. We have placed the sensor outside the motor, which is capturing the shaft position. There will be one mark which is there, so it will be captured that mark always. Okay. So now some paper or some dust on maybe on sensor or some obstacle, half of the sensor is not visible, half of the shaft is not visible. Okay, then that time what sensor will sense? It will be half of the data only able to sense. Okay, it will not sense the accurate one. Then it will send the feedback that actual speed which is we are comparing with the reference one. So the actual speed must be track the actual one. Then only error will be approximately zero. Error cannot be zero, approximately zero. Okay, our aim is to make the error zero, but we will make the approximately zero. Okay, because always some charging will be there, because this is a machine which run, so friction effect will be there, vibration or friction effects will be there, little bit vibration will be there. Okay, so our aim is to make the approximately error zero. Okay, so this sensor send the feedback of half of the data. We are running at 1500 rpm, but it will send the 600 rpm
Wrong data.
wrong data. Then what would be the error? Error will be the huge. Okay, so error will be the huge. Then it will say the controller, this is the error. Then Q means optimize the voltage vector to compensate this much error. Okay, but our model already working in a proper condition only. But because of the faulty sensor sensing result, we are making the burden on the controller. We are making burden on the motor. So now the what controller will see, the controller will optimize the different voltage vector. Okay, but actually that is not required basically. So and this is the civil.
He said in the morning class, predictive controller. He implemented it.
This is that paper.
This
Huh.
model.
Model PTO. This, one PhD given on model PTO and other PhDs are working now.
Any vehicle it is implemented.
No, we will implement. Hardware we have implemented, but the industry we have not tried.
Commercial is not.
So this is the with the model PTO only. So these are the results of simulation, and we have also experimental setup. Okay, so here 2 level and 3 level routine, and this is also mentioned the funding because we have taken the help of the DST. Okay, so these are the publications, and the recent publications we have. Uh, so this is the what 2023, and there are other recent 2025 recently published, but I didn't bring here. So I think it is missed. And so these are the my publications, and you can ask me anytime if you have any doubts. You can have my papers in the Google, and Google Scholar also. There are my papers available. So at any point of time, you can contact me, and my mail ID is tramesh.we@gmail.com. So if you need any support in TMSM guide simulation or hardware implementation, then you can ask me anytime. So if there are any further questions, so you can ask me through email also. Okay. So with this, I'll stop here. Okay. Thank you. మీరు అని చెప్తాను.
Dear participants, we will break for tea. Sorry, isn't it?
You- 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 you-
తీసినారు అదే అదే తీసుకోలేదు పాయింట్ అక్కడ
పాయింట్ ఎక్కడ ఉంది?
అది వేరు
ఏంటంటే
అది వేరు ఆ పాయింట్ వేరు
మూడు కూడా అవ్వలేదు ఇంక పెట్టినట్టు
సెట్ చేయొచ్చు, అది వచ్చేసిట్టున్నారండి. సెట్ చేయొచ్చు సెట్టింగ్స్ లా.
Dear participants, we will have an article discussion. Please uh, gather in a single group. So, please check the recent papers of Dr. T Ramesh sir. Recent papers like the 3-level inverters and 5-level inverters applied to the permanent magnet synchronous motor. Just go through the papers and abstracts and introduction and conclusion, and what are the methodologies proposed. So what are the comparison between the simulation results and hardware results. So please go through, and if you have any doubts, please ask. So see how the sensorless method, then model reference adaptive control system method, and then fuzzy logic methods, how they are implemented, and again in the fuzzy logic type 1, type 2 methods, please go through. Hello. Uh, uh, చెప్పండి. ఏం చేయలేదండి.
Sir, actually, I have one doubt, sir. I know normal order like proportional unit controller, derivative controller, like PID controls I know. Fraction order control means what, sir? Is it actually
Oh, yes. These fraction order systems, they will be having order between 0 to 1 or 1 to 2 non-integer values. Like decimal values are also allowed. Like if you take integrator, so it will be 1 by s.
yes, sir.
So, but in the case of fraction order, it will be 1 by s power 1.2, 1 by s power 2.1, 1 by s power 0.8, 0.85 like that. So, what is the advantage is you will have the choice on the integral action. Choice on the integral action. That means if you say 1 by s square, it is a full integral. So, if you say it is a s power zero point 0.5, it is a partial integral. That is the strength of the integrator you are controlling.
Okay.
Instead of making it as a full controller, full integral controller, I am making a partial integral controller. So the strength can be varied. The strength of the integrator can be varied. So that is the choice.
So similarly for derivative control.
Yes, similarly for the derivative controller also you can increase the order from 0 to 2. Any values you can change. So the same things you can implement for the your instead of PI controller in the 3 level or 5 level multi level inverters. Instead of PI controller, you can use the fraction order controllers also for implementation purpose and generating the control signal.
So there are advantages using fraction
Yeah,
order.
fraction order control. Like the advantages are the stability margin will be improved. So normally in the control systems, what we will do? Only the left hand side is stable, right hand side is unstable. But using this fraction order controller, in the right hand side also you can extend the control action, and which will be stable also.
Okay.
Using that is the main advantage. And then robustness is also one important property. Even though the system parameters changes, suppose the system gain changes, time constant changes over the time, the controller will be giving the satisfactory performance.
This fraction order control.
Fraction order controller. So the performance is robust over the changes in the gain of the system. That is one advantage. And phase margin, gain margin, it will have high values. Phase margin and gain margin will be having high performance. Like that.
Suppose if it is normal controller, sir, then suppose if you are getting s power 1 in the denominator,
Yes.
then we can say that there is a pole at origin.
Oh.
Suppose s square is coming,
Yes.
then we will say there are two poles at the origin.
Yes.
Suppose if we are adding fractional integral controller,
Yes, yes.
then we will get s power 0.4, 0.5.
Yes, yes.
Then if someone asks me to locate the pole, then how can
Yeah, for that, actually, we have to define the integrator or differentiator using special derivation.
Okay.
Special definitions are available.
Okay, okay.
RL definition, like that, special derivatives are there.
So like this we cannot represent.
Yes, you can't represent with a single pole.
Okay, okay.
So you have to use approximation, frequency domain approximation. That means integer order controller having the same frequency characteristics as fraction order controller. You have to take one approximation, and from that approximation only you can draw the pole zero diagram. If you want to draw the pole zero diagram.
So these controllers also we can tune like normal PID,
Yes, yes,
APK,
yes, yes,
KD,
yes.
we used to tune with PSO some algorithm.
Yes,
Optimization technique.
yes.
So here also same
Yes,
thing we can do.
here also we can tune using PSO or GW,
Any optimization.
GWO or WOA,
Okay, okay.
neural networks, fuzzy logic, all the soft computing and swarm intelligence techniques you can implement for the fraction order control also. And only thing is, apart from KP, KD, you will have two more parameters: the power of integrator, power of differentiator. So total 5 parameters will be there instead of 3 parameters. This you verified on the physical system also, not only simulation.
Okay.
On the hardware results also I obtained in the NIT Trichy laboratory.
Okay.
There is a two tank system is there, level control of the tank, height of the tank. So the Simulink which I have developed using the fraction order controller, the same thing using a data acquisition card. I interacted with the hardware and implemented the results and published the papers also.
Okay. Normal PID controller
Yes,
and fractional.
fraction order control. The performance, both controllers.
Implemented fraction
Yes,
order.
both controllers are implemented, and performance of the fraction order controller is found to be better than the integer order controller. And both experimental results and simulation results verify that the fact is correct.
Actually, in theory, we say that, sir. Maybe we are adding maybe proportional controller. We will simply mention KP.
Yes.
Suppose we say adding derivative controller. We will mention one box KT.
Yes.
Like
Yes.
that. I am having doubt actually.
Okay.
What in physically, practically? Suppose adding pole means theoretically we will add in one box in the
Yes.
signal program or whatever it is, we will do.
Okay.
But practically, we adding controller means what, sir? What they will do? That is my doubt actually.
Okay.
It's like interaction.
Hmm.
Maybe analysis we will do,
Yes,
adding
yes.
code, maybe
Yes,
we
yes,
will improve
yes.
the stability. Like that. Actually, this is my I doubt since my BTech I am trying, but I could not find the answer. మనం మామూలుగా థియరీ డిస్కస్ చేసినప్పుడు ఏం ఏమనుకుంటాం ప్రపోర్షనల్ కంట్రోల్ యాడ్ చేయండి ఇంటికల్ కంట్రోల్ యాడ్ చేయండి స్టడీ స్టేట్ ఎర్రర్ జీరో అవుతుంది థియరిటికల్ మీరు ప్రాక్టికల్గా సపోజ్ జీరో కేసు మేబీ వాటర్ లిక్విడ్ సిస్టమ్ కావచ్చు ఇంటికల్ కంట్రోల్ యాడ్ చేస్తున్నాం అనుకో అంటే ఏం యాడ్ చేస్తున్నట్టు మనం అసలు బేసికల్గా
By adding integrator, you are increasing the order of the system.
Okay.
Order of the system. Higher order. You are making it as a higher order.
higher order.
It's the only physical explanation you can say.
normal discussion, sir. Suppose we are discussing PID controllers, na? Suppose what frequency control is it? Oh. Oh. suppose maybe low frequency అట్లా anything sir, anything కూడా we are controlling like this sir. Suppose this deviation ఉంటుంది, మనం ఒక set of values KP, KI, KD values తీసుకున్న ద్వారా చూపిస్తాం. maybe 1, 2, 3 values చూపిస్తాం. మనకు డిస్టర్బెన్స్ ఎంత అయ్యాలంటే డెల్టా KD అనేది స్టెప్పింగ్ సార్. డిస్టర్బెన్స్ 1 ఏంటి ఈ వాల్యూస్ మనకు మేబీ కరెక్ట్ ఎర్రర్ 0 వచ్చేసింది. ఇది ఎర్రర్ సార్. డిస్టర్బెన్స్ అనేది సపోజ్ 2 యూనిట్స్ మేబీ మన కంట్రోలర్ ఈగా పిలిస్తే రెస్పాన్స్ ఎలా వచ్చిందా 0 వచ్చిందా
ఎర్రర్ పెంచారు కదా,
డిస్టర్బెన్స్
పెంచారు ఈ సాటిస్ఫై అవ్వకపోవచ్చు.
మేబీ రావచ్చు రాకపోవచ్చు. మేబీ స్లో
ఎర్రర్ బేస్ చేసుకుని మనం కంట్రోల్ చేస్తే ఆయనకే సూటబుల్ అర్థగల ఎర్రర్ మారిందంటే కంట్రోల్ సిగ్నల్ మారాలి. ఈయన బట్టి ఇవి వస్తాయి, ఇవి బట్టి కంట్రోల్ సిగ్నల్ ఇవి అంటే
ఒకవేళ కావచ్చు
రావచ్చు. సరే సాటిస్ఫాక్టరీగా ఉండొచ్చు, యావరేజ్గా ఉండొచ్చు, ఎక్సలెంట్ పర్ఫార్మెన్స్,
రెస్పాన్స్
కొంచెం ఆస్ట్రేట్ స్లోగా ఉండొచ్చు, ఆస్ట్రేట్ ఎక్కువ ఉండొచ్చు.
మ్యాక్సిమం మనం కంట్రోలర్స్ డిజైన్ చేసుకుంటాం సార్. నార్మల్ కింద పేపర్స్ మ్యాక్సిమం స్టెప్పింగ్ డిస్టర్బెన్స్ లేదంటే 1 మినిట్ 2 మినిట్స్ తీసుకుంటాను. మ్యాక్సిమం టైం డిస్టర్బెన్స్ అంటే 90% తక్కువ తీసుకుంటాను.
ఎక్కువ స్టెప్ తీసుకుంటూ అది కూడా
తీసుకోమని
ఇన్పుట్ ఏదో వచ్చినా డిస్టర్బెన్స్ జనరల్గా స్టెప్ డిస్టర్బెన్స్ ఇస్తారు సార్. ఆస్ట్రేలియన్స్ కూడా తీసుకుంటారు వాటి మీద తీసుకున్న డిస్టర్బెన్స్ స్టెప్ డిస్టర్బెన్స్
అనాలిసిస్ కోసం స్టెప్పే పడతాను.
సైఫర్డ్ ఆస్ట్రేషన్స్ ర్యాంప్ వారు తీసుకోవచ్చు.
అదే సార్ అనేది ఏంటంటే ఇప్పుడు మనం స్టెప్పింగ్ PET వల్ల సెట్ చేస్తున్నాం. సపోజ్ నిజంగా స్టెప్పింగ్ వర్క్ చేస్తున్నాం. ఇప్పుడు సపోజ్ ఆ ఇన్పుట్ డిస్టర్బెన్స్ టైం వేరింగ్ అవుతుంది. మీకు
టైం వేరింగ్ అయినప్పుడు సెట్ కాదు, దాని వల్ల మీరు కంట్రోల్ మార్చాలి. డిస్టర్బెన్స్ మారిన వల్ల కంట్రోల్ సిగ్నల్ మార్పు డిస్టర్బెన్స్ బట్టి సిగ్నల్ మ్యాగ్నిట్యూడ్ పెరగడం వల్ల హై కంట్రోల్ యాక్షన్ ఉంటే కానీ సెట్ కాదు. అలాంటి పరిస్థితుల్లో సార్ మీకు కంటిన్యూస్గా టైం వేరింగ్ అంటే ఎంఆర్ఎస్ మోడల్
అడాప్ట్ చేసుకుంటాం.
ఆసిలేషన్ ఉన్నా కూడా వర్క్ చేస్తారు మోడల్ ఎంఆర్ఎస్ అడాప్టివ్ కంట్రోల్.
ఓకే సైడ్
మోడల్ రెఫరెన్స్ అడాప్టివ్ కంట్రోల్ ఎంఆర్ఎస్ మోడల్ ఎంఐటీ రూల్ అంటారు. ఎంఐటీ రూల్ బేస్ చేసుకొని అది కరెక్ట్గా వస్తుంది. ఆసిలేషన్స్ కూడా
డిస్టర్బెన్స్ ఎలా ఉందంటే
కంటిన్యూస్లీ వేరింగ్ డిస్టర్బెన్స్ ఆల్సో సిగ్నల్ సార్ ఎర్రర్ బేస్ చేసుకొని సిగ్నల్ కాంపోనెంట్ వోల్టేజ్ కరెంట్ కానీ
అదే సీరియస్
కంట్రోల్ అంటే ఫిజికల్ అకౌంట్ అంటారు. ఆపరేటర్ కానీ లేదా ఎల్సీ కంట్రోల్ కానీ అలాంటి ట్రాన్స్ఫర్ ఫంక్షన్ అలాగే కంట్రోల్ నోటేషన్ ఎంఆర్ఎస్ ఎంఆర్ఎక్స్ ఫర్ ఎల్ఎఫ్సి ప్రాబ్లమ్ ఎంఆర్ఎక్స్ ఫర్ ఎల్ఎఫ్సి ప్రాబ్లమ్ మోడల్ డిఫరెన్స్ అడాప్టివ్ కంట్రోల్ ప్రిడిక్టివ్ కూడా వెళ్ళారు కన్వర్టర్స్ ఎంఆర్ఎక్స్ మోడల్ డిఫరెన్స్ అడాప్టివ్ కంట్రోల్ ఫర్ ఎల్ఎఫ్సి ప్రాబ్లమ్
ఎందుకంటే కంట్రోల్ అంటే నార్మల్ కంట్రోల్స్ ఏమైనా కన్వెన్షనల్ కంట్రోల్స్ ఏదైనా సరే పారామీటర్స్ మారు కంట్రోల్ పారామీటర్స్ మారినాయి అంటే అది అడాప్టివ్ కంట్రోల్ అంటారు. ఏపీ వన్స్ మీరు డిజైన్ చేస్తే ఫిక్స్డ్ వాల్యూస్ చేంజ్ అవ్వదు. 2.1 3.1 అది కంటిన్యూస్గా చేంజ్ అవుతుందంటే అది డివియేట్ కంట్రోల్ కాదు. దాన్ని అడాప్టివ్ కంట్రోల్.
So, dear participants, I thank you for your active participation in the article discussion. Hope the today's sessions are useful to all of you. So, we are closing the today's session, day 2 session, and tomorrow we'll meet at the morning 9:30 a.m. The tomorrow session will be Dr. Dugga Ravindra sir from NIT Allahabad. So, thank you.